Okay, welcome to you all for this webinar on panel design. Here, the intention of this webinar study here by keeping your end examination preparation tips followed by concepts. Before moving to actual, as here first, what we are going to cover in this of the entire of this subject depends on phases of the phases we are entire of this subject. We will study about those. As you already know, briefly we will review all the page is called as lexical analysis. Second one is called as syntax analysis or parser. One is called as semantic analysis. One is called as is code optimizer. First one 6. Phase wise here diagram followed by what is the input and the output. After that, we discuss some more details about its role, analyzer called as Lex tool, and later we will discuss about the second phase syntax analysis. There are two types of examination point of view here of comparison. The parser we are having many of them address those parsing the problem. And bottom of parsing we are having LR Parser types of detail we will discuss end of this session, so we can able to solve problem. So let us recall once the introductory concepts definition.
Sir, excuse me, sir.
Yes, sir.
Sir, your voice is very low, sir.
Oh, are you hearing now? Is it okay now? Can anyone respond?
So good morning, sir. Sorry to disturb, sir.
Madam, now it
Now
is
it
okay.
So now it is clear, sir, but there are some disturbances in your network, sir.
Here networking is there, madam. Try to
I mean, some other sounds are interrupting this session, sir.
anyone unmuted. Can you check it, madam? I hope no sound is coming.
Okay, sir. Now it is clear, sir. Thank you, sir.
Okay, sorry for the inconvenience. Let us move to the what is a compiler that everyone aware of the compiler. So without knowing much about compiler also, indirectly we are using the term compiler as a computer science student. So in first year you may studied C language, and second year you may studied C++, Java, followed by various programming languages. So any programming language, whenever you are writing a program, what you have to do as per the syntax of the respective programming language, you can write the program. After completion of writing the program, what you have to do? You have to first compile the programs. Term compile. So without compilation, we can't move ahead further. So what the compiler will do? Compiler will read the program and will check the syntaxes and also finds any errors are there. After rectifying all the errors, etc., the program is successfully compiled. So then that source program is converted into some other form. For example, if you will compile C program immediately after compilation, let us see in your folder wherever you saved the program .c. So then immediately after compilation, successful compilation, you will get some obj object file .obj. After compilation only that object file is created. That means your source program is converted into some other form. So that can be done through compilation only. So once compilation is successful, then what you have to do, you can run your program. So during running, you will see the output. Whatever the given input, the output is produced accordingly. So that is actually the process of compilation. So finally, a compiler which converts the source program into target program, maybe high level to low level, then low level to machine level, like that. Finally, our intention is, so the source program is converted into machine level language. Why? Because the computers understands only the binary language, that is zeros and ones. Any given language that can be converted into target language. Target language is our machine level language. So that is the process of compilation. So in addition to compiler, here we are having interpreter also. Let us see the differences between these two. First, see some definitions of compiler. So here a program, we are having a program, just now we discussed about C. For example, program which accepts input, a program text. So whatever the program we have written in the form of some source string or some high level format, etc. So in a certain language, then produces output. So it produces output of that program, again text format in another language. So the output can't be in the same language what you have written, the programming language. The output can be in other form. So whenever converting input to output, here one important point has to preserve the meaning of text. So that means suppose you have given some input, so then it has to produce the outputs accordingly correctly. So it won't change the meaning. For example, your program is addition of 10 numbers. You have given 10 numbers. So the output should be compulsory. It should add all the 10 numbers. So that logic should be preserved like that. So this is one definition. Then coming to our compiler design, regularly used definition by our prescribed textbook Aho et al. A program that reads a program written in one language. So whatever the program that can be written in one language, that language is called as source language. That means our input language. And translate it into an equivalent program in another language. Now what is the another language? Target language. Now here our source language is the input. Then we have to convert into target language. So for this, how this will be done here, we'll use the compiler. The compiler is a translator which converts source language into target language. That is the simple form of definition of compiler. Then what is an interpreter actually? So here also a program that reads a source program produces the results of executing this source. So immediately, so compiler, the entire program that can be converted into, directly it won't convert into our target language, some intermediate level. Like step by step, it converts one form to other form by depending on various internal connections. Those we will call it as phases actually. Whereas interpreter, so line by line it verifies, then it produces what is the final output by seeing the execution. It won't see phase by phase. So completely after execution only it produces. The program that reads source program produces the results directly of executing this source during execution. So here we deal with compiler. So many of these issues arise with interpreters also. So you already aware what are the differences between compiler and interpreter. So those you can, maybe for short answer question, you will get What are the differences between compiler and interpreter like? So you can prepare that question. For short answer, part A as per our exam pattern. Okay, now let us see some examples of compilers. So this diagram, just now what I explained, here you can see the role of compiler. We can take input that can be written in source program that can be converted into our target program. Here, this is the role of compiler. Source program is converted into target program. For example, here some examples of compilers are C is a typically compiled programming language. Then Lisp is another programming language. This is interpreted, not compiled. This is typically interpreted language. Then Java, everyone aware of the Java, is a compiled that can be converted into bytecodes. Further, those are all interpreted. Some other examples also like C++ to Intel Core to assembly language, then C++ to C, then high performance Fortran to Fortran. This is parallelizing the compiler. Then C to C, that means any language to itself, self. So these are all some of the examples of compilers followed by interpreter also. Okay, now let us see what are the qualities of a good compiler. So many compilers are there. So any compiler may needs to satisfy some good factors. Then you can say there is a good compiler. So what qualities would you want in a compiler? Our first target is first and foremost, it has to generate the correct code. So then it generates whatever the code that can be executed fastly. Then conforms to the specifications of the input language. Whatever the input language, so it should be satisfies the specifications of the input language. And it copes essentially with arbitrary input size, variables, etc. The size also considered here without wasting unnecessary size. Then the compilation time, so it is proportional to size of the source code, that is linearly. Then good diagnostics, that means it produces whenever errors are occurred, then errors can be diagnosed, rectified. Then consistent optimizations. So whenever you are optimizing a code, some consistent methodologies you have to maintain. And also works well with debugger. So these are all the some of the qualities of a compiler. If any compiler may address all these qualities, then you can say that compiler is of a good quality. So any programming language, whatever corresponding compiler we are using, so compulsory, so it has to satisfy some qualities. Then let us see, there are some principles of compilation. The compiler must preserve the meaning of the program being compiled. The first point we already mentioned. Whenever the source program is converted into target program, that is input is converted into output, compulsory it has to preserve the meaning. So then improve the source code in some way. There are some other issues also depending on the setting, that is the speed of compiled code, then space, size of the compiled code, then feedback, information provided by the users, whoever using, then debugging, the transformation substitute the relationship source code versus target, debugging at the time of rectifying the errors. Then a compilation time efficiency, whether it is fast or slow compiler. So all these issues needs to be addressed. These are all some principles of compilation. Okay, then let us see some applications or uses of compiler. So where actually compilers are used, then followed by some applications. Most common uses for translation purpose, translating high-level programming into object code. For example, program translation, there is binary translation, hardware synthesis, etc. Then optimization for computer architectures, which improves program performance, take into account hardware parallelism. Because of this, these are all advantages. Then automatic parallelization or vectorization. Then performance instrumentation, example, -PZ option of CC or GC. These are all available the compilers in Unix or Linux flat operating system. Then interpreters like Python, Ruby, Perl, MATLAB, SS, etc. Then software productivity tools like debugging aids, example Purify. Then security using some Java virtual machine which uses compiler analysis to prove safety of Java code. Then some text formatters like just-in-time compilation that we will call it as JIT compiler for Java. Then power management, then global distributed computing, etc. So the key is here ability to extract properties of a source program, that is analysis part, and transform it into to construct a target program, that is synthesis part. In the entire of compilation part, we are having two parts, analysis part and synthesis part. Analysis part that is related to source program, then synthesis part that is related to our target program. Now let us see some applications of compiler or compiler technology and tools. So here for parsing XML, extensive markup language, and other to generate documents, code, etc. Then parsing some domain specific and device specific languages, and implementing a server which uses a protocol such as hypertext transfer protocol or IMAP, etc. Then natural language processing is one of the emerging area in nowadays. We are talking about artificial intelligence, so data science, machine learning. Here natural language processing also plays important role in this emerging area. For example, spam filter, search, and documentation comprehension, summary generation, etc. Then translating from a hardware description language, HDL, to the schematic of circuit. This is actually EC related. They are having VHDL, PLSI, etc. For hardware also, this will be used compiler. Then automatic graph layout like GraphBeach. This is one example for this. Then extending an existing programming language to other languages by incorporating some of the features. Then program analysis and improvement tools. These are all some of the applications of compiler technology, and so these are all some of the uses and applications of compiler. Now move to what is the structure of the compiler. The general structure of a compiler. Now we know what is the compiler, which converts the source code into object code. Here, whenever converting the source code or source program into target or object code, during this process it encounters errors also. Okay, now this is the general structure of a basic compiler, which takes input as source code and produces output as the target code or object code. Then during the compilation process, it generates errors also. Then the compiler, good qualities of compiler just now we addressed. It must generate correct code. It must recognize errors, and analysis and synthesis part. Analysis is related to source program. Synthesis is related to target program. This is the role of compiler in the compilation. Okay, now move to, there are some phases of compiler. So according to this structure, source code is converted into the object code or target code. Directly it can't convert in single step. We are having various phases. So this is the one important question in first unit. In examination you may get this question. Explain various phases of compiler with neat block diagram, or explain the phases of compiler with phase-wise input and output by taking one example, or they will give one example. So translate the given source program into target program by producing phase-wise inputs and outputs, like any of these questions. So first, this is the block diagram of phases of compiler. In the compiler, we are having total 6 phases. So all the 6 phases, order needs to be maintained. We can't change the order. So the first phase is called as lexical analysis, also called as scanner. The second phase is called as syntax analysis, also called as parser. The third phase is called as semantic analysis. Then the fourth phase is called as intermediate code generator. Then fifth phase is called as code optimizer. This is optional phase actually. Then the sixth phase is called as code generation. So all the 6 phases, we need to maintain the order. We can't take the last one be the first one, middle one be the last one, like that. The order should be follow. The same order. First lexical analysis or scanner, second one syntax analysis or parser, third one semantic analysis, fourth one intermediate code generator, fifth one code optimization, sixth one code generation. So all phases are internally connected. So here you can see all this, you can make it as one box. So now you can see our previous diagram, what it will be. So this will be like this. Now this entire box is compiler now. This box is compiler. What is the input? Source program. What is the output? Target program. In the previous diagram, whatever, the simple structure, same only. But internally, the compiler is divided into 6 phases. All the 6 phases are given in the order, whatever the order. So same order needs to be maintained. Okay, now for each phase, so we have to take the input. So then for first phase, the input, the source program is converted into some intermediate representation. Now that is the output of first phase. Now output of first phase becomes input of the second phase. Then second phase takes output of first phase as the input and produces some output. Then that output will be treated as input to the next phase, like that. So one phase input should be the, one phase output should be the input to the next phase, and so on. Then finally coming to the last phase, the code generation. Its input is output of the fifth phase, that is code optimizer. Then finally, what is its output? Our required target program. This is our required target program. We have taken input as source program. Source program is converted into target program. This is our required target. So how this will be converted in different phases? Okay, now each and every phase in the previous diagram, there we are having error also, error component. So that's why here every phase encounters or occurred errors. Those can be handled by using error handler mechanism, using some error recovery strategies. Phase wise, whatever the errors are encountered, there are some error handling mechanisms. So commonly the error handler is connected to all the phases. In the diagram you can see. So all the 6 phases are connected to the error handler. Then in addition to this, we are having another component which is called as symbol table. This symbol table will be treated as the data structure. So which is used to store the information about the phase wise. The phase wise, the information related to the program, some important information like variables, that means identifiers, some constant information in the memory where those are all stored, that location, etc., that can be stored by using symbol table. That's why this will be considered as data structure. This is also connected to all the phases. Whichever the phase, whenever it requires the information about the identifiers or whatever the information available in the program wants to access, so it can access from the symbol table like memory where it is stored, in which location it is available. So this is the block diagram or functional diagram of phases of compiler. So here briefly I will explain phase wise what is the input and what is the output. So by taking one example, so let us take for example x equal to y plus z into 10. So this is the source program. This is the source program which is called as input. Okay, now first lexical analysis. So lexical analysis or scanner, what it produces, it reads or scans the input string or input program from left to right and identifies in the given source program what are the things presented. So that means these can be grouped. The sequence of characters are grouped into one category that we will call it as token. It produces token as the output here. So what is token? Sequence of grouping of characters. For example, identifiers, then constants, then keywords, then operators, etc. These are all the frequently used tokens. So in your given source program, let us see. Here we are having x, y, z. What are x, y, z? These are all the variables. Now these variables, now we'll call it as identifiers. So x we may call it as ID1, y will call it as ID2, z will call it as ID3. Now we are having equal, plus, into. What are these? These are all called as operators actually. We are having equal is assignment operator, plus is addition operator, then asterisk is multiplication operator. Then we are having a number 10. So what is this number is called as? This is constant here, 10. So like that, the lexical analysis or scanner which reads the source program from left to right and identifies in the source program what are the tokens available. Then it groups all the related tokens into one group. So all identifiers are one group, then all operators are one group, then all constants are one group, like that. This is the output of lexical analysis or scanner. So that is called as token. So now here this is the output of the token. Now this token will be considered as input to the second phase, that is syntax analysis or parser. Then what syntax analysis or parser produces? The tokens that can be represented in the hierarchical form, that is called as a tree structure. Tree structure. This tree will call it as what we will call it as parse tree. We'll as parse tree. We are having another tree also, syntax tree. But these two are different. Parse tree and syntax tree both are not same. So parse tree is nothing but for the given grammar. So we are having a grammar in syntax analysis or parser. So the programming languages are described by a grammar which is called as context-free grammar. That also we'll review briefly. So from the grammar, if you want to derive a string using the productions, so the process of derivation, so step by step, whatever the productions we substituted, that can be represented hierarchically in the form of tree. The tree is called as derivation tree or parse tree. Then without using the grammar, by considering only the string, you can construct a tree, then that is called as syntax tree. So syntax tree hides the grammar symbols. Only it contains the terminals. So that is the difference between a parse tree and syntax tree. Okay, now the tokens here you can see here there is no topic of grammar. So this expression x equal to y plus z into 10, this can be represented in the form of tree. Now the tree is called as syntax tree. So the output of syntax analysis or parser, so abstract syntax tree. Why you are calling it as abstract syntax tree? Hiding. So it won't shows the grammar variables. Only it shows the terminals in the form of string. So it is called as abstract syntax tree, in simple terms AST. That is the output of syntax analysis or parser. Okay, now what semantic analysis will do? Will take input as the same syntax tree, whatever we constructed from the syntax analysis or parser. Then it provides some semantic actions, some validations. Suppose you are having in this expression 10 is there, 10 actually constant. What is type of this constant? Whether it is integer value or floating value. So what is this conversion, like into to float or something? So the type conversion is not there here. Directly a constant is there. It provides the semantic checks or validation, meaningful form. So that is the output of semantic analysis. That we will call it as annotated abstract syntax tree. In the syntax tree, wherever the respective values are there in the particular node, it can be labeled. Annotation is nothing but labels. Labeled the meanings or the semantic checks in the respective nodes wherever that value is there. For example, in the tree 10, where the 10 is connected in the tree, in that node, it gives some the type conversion like into to real or into to float something. So this is the semantic check or validation. This type of Validations or checks can be done by semantic analysis. Again, output of semantic analysis is also same syntax tree only, but annotations are added. That is the only difference. Okay, now the next phase, intermediate code generator, what it takes? It takes the annotated abstract syntax tree constructs. Those can be converted into some intermediate form. So the output of intermediate code generation is called as intermediate representation. So what are the various intermediate representations? Even the abstract syntax tree is one intermediate representation. There are some other intermediate representation also, like 3-address code. So 3-address code, the general form is x equal to YOPB, YOPZ. Here y and z are operands. OP is the operator, then X is the resultant operand. So here 3 addresses. So one address for Y, one address for Z, one address for result X. That's what this is called as 3-address code. This is general form of 3-address code. In 3-address code, we are having various representations like triples, then quadruples, then indirect triples. So 3 types of 3-address codes are. This is very important in intermediate code generation. In examination, you may get explain various 3-address code forms with an example, or for the given source program, convert into 3-address code with quadruples, triples, indirect triples. So this question is important there. These are all various intermediate representation forms. Okay, now these intermediate representation forms. So if you are having some repetitions, some duplications are there, so those can be reduced or optimized. For that, code optimization is used. What code optimization will do? Wherever the possibility to reduce the some of the temporaries or the variables, so it can be optimized and produces the same as intermediate code form only, but optimized intermediate code. So once you know the intermediate code output, the code optimization output also same, but some lines may be reduced or merged with others. That is optimized code. So whenever you are doing optimization compulsory, again the meaning has to be preserved. So that is the code optimization phase. Then finally, what the code generation will do? The code generation takes the optimized intermediate code as the input and produce the target code. The code generator directly it can't produce machine language. The target program that can be written in assembly language program by using assembler. By using assembler, it converts assembly language programming into machine level language. So using compiler directly, we can't produce machine level language. So we can produce output as in assembly language. Using assembler is the another compiler which converts assembly language program into machine level language. This is your real target programming language. That is our machine language. So this is the process of compilation. Now you can see phase wise the given input, how it is converted into some intermediate representation, then finally how it produces the output. So for any given example, like they will give one string or one expression or one programming syntax that you can convert into phase wise like this. This is an important question. Diagram followed by phase wise input and outputs. Okay, the same whatever I explained here I have given. I skipped all this because we'll concentrate more on the problems. So anyway, I will share this PPTs also. You can go through later if you want. Here you can see the parse tree also I explained. Just see one example here. So parse tree for the expression. Actually, this is b square minus 4ac. That means here the expressions any powers you can expand like b into b minus 4 into a into c. So one expression. What we have considered x equal to y into z plus 10, any expression we can convert into it parse tree. So whenever if you want to construct parse tree, compulsory grammar is required. That is context free grammar. For syntax tree, grammar is not required. Only expression is required. So actually here the grammar is in our simple terms. I will write here. This is called as arithmetic expression grammar. E equal to e plus e, then e derives e minus e, then e derives e into e, then e derives e by e, something like this. So then you are having E derives T term. Then T derives T into F. Then F derives E within parentheses or some identifiers or constant, etc. like this. This is the actually arithmetic expression grammar. So here the string is b square minus 4ac. For this, if you want to draw its derivation tree or parse tree, so here first you can take the starting variable as the root. Now E is the root. Here whatever contains, your expression contains minus actually. So first you can take the expression related to minus this one. You can connect E minus E. So all the internal nodes you can include within circle. Then leaf nodes which contains terminals, we can't include circle. Now here you can see left hand side of minus what you want, b square actually. So b square means again what is this one, into expression you want, E derives, actually you want E into E. So then before into left hand side of into what you want some identifier. Then the right hand side of the into also identifier. So you are having E derives T, then T derives F, then F you are having identifier. Now the identifier is B here. Similarly E derives T, T derives F, then F derives B. Now you can see B into B. Here B square minus, then what you want, again you want into, so 4 into A into C. So again you want into expression here. We are having E into E. So left hand side of into what you want. So again here you are having here you can see T into F. Why? Because you are having constant also, where the constant is in F. So here again you can take E derives. So E derives T, then T derives what you want, T into F actually. Now here before into what you want actually 4 you want. So T derives F. Now F derives, we are having identifier as constant also. So directly you can take the 4. Then 4 into again what you are having, F derives ID. So what is this one, A. So again into your E derives T, T derives F, F derives identifier. What is the identifier here, C. Now you can take all the leaf nodes from left to right in this tree. First what you are having, B into, so B into B, this one. Then minus, then the leftmost one is 4, then this one is into, then A, again into C. Now you can see our input string is derived here. Now this is called as derivation tree or parse tree. Here in detail explanation is given. This is simplified form. By taking leaf nodes from left to right, you will get the string, whatever the string. This is the derivation tree or parse tree. Now for this, how to construct the syntax tree? For syntax tree, here the variables are hidden. It won't show us the variables, it shows only the terminals. Here you can see b square minus 4ac. Only for this expression, the syntax is constructed here. Grammar is not required. So here, first we have taken any one as the root. Now here you can see b square minus 4ac. So minus is the middle one. So now minus, you can consider it as the root. So minus of the left hand side, what you are having again into operator. So here one point you can remember, the root and all internal nodes are labeled with operators. Then all the leaf nodes are labeled with the operands. Here you can observe. So minus is the root node. Then into is another interior node. So minus left hand side into, again it has B into B. Left child is B, right side also B. Then after minus right hand side, again we are having 2 intos, 4 into A into C. So again you can take into as the interior node. Left hand side of this, for example, again into 4A, then right hand side C. Now this is called as syntax tree. Now you can see the previous one is derivation tree or parser. This is the syntax tree. The differences between these two you can observe carefully here. No grammar is used here. Only the string is used here. So in the derivation tree or parse tree, the root and internal nodes are labeled with grammar variables, and leaf nodes are labeled with terminals. Whereas in syntax tree, the root and internal nodes are labeled with operators, then the leaf nodes are labeled with operands. So this is the difference between derivation tree and parse tree. So this abstract syntax tree is actually one of the form of intermediate representation. The intermediate code fourth phase. So what is the output it produces? So one of the intermediate representation is this abstract syntax tree. Then semantic analysis, we already mentioned. What it provides, semantic checks, context handling. So collects the context means semantic information, checks for the semantic errors, and annotates means labels nodes of the tree with the results. For example, type checking is one of the important concept. Report error if an operator is applied to an incompatible operand, and also check flow of controls, then some uniqueness or name related checks. These are all some of the examples of semantic actions. Then intermediate code that we already explained, that annotated abstract syntax tree constructs that can be converted into some intermediate representations. Abstract syntax is one of the intermediate representation. In addition to, we are having 3 address code, just now we explained. So this is one example, the same b square minus 4ac. This is the 3 address code form for this. First we have taken that constant in one temporary that can be multiplied with a, that is temp1 into a, that is stored in another temporary. So then that can be multiplied with c. So this one into c, that can be stored in another temporary. So then the left hand side b into b, that can be stored in another temporary. Then the temp5, the result equal to this one, temp4 minus temp3. This is the actual 3 address code. This is one intermediate representation. So here some temporaries may be removed. Why? Because here 1, 2, 3, 4, 5 temporaries are used. So here instead of, for example, here temp1, directly you can take some 4 into a as temp1. Then one temporary is optimized, like wherever possibility. So you can optimize the temporaries. Then that is called as optimized intermediate code. That is 3 address code. That is the code optimization. So then finally code generation. In code generation, what we will do, that optimized 3 address code that can be converted into assembly language program. Directly we can't convert into machine level language. So it converts into assembly level language. By using assembler, we can convert assembly language into our machine level language. So this is the code optimization, just now whatever we explained. It takes the front end, then output of the front end intermediate representation. So optimizer is the middle end, which is optional actually. By default, optimization taken place. Again, it produces same intermediate code with optimization. Then backend, what it takes, the optimizer code is converted into target code. Here the target code is in assembly language program that can be converted into machine level language using assembler. So this diagram shows the role of code optimizer in the compilation mode. Okay, now then coming to, okay, this is the detailed explanation about all the phases with example. Then code generation, first it produces assembly language program by using some basic code generation algorithms. Okay, now we'll move to the lexical analysis phase. Some important concepts we will discuss. So before that, let us see some more points related to symbol table. In the compilation model, we have seen the symbol table. One example here you can see, I told at that time, the symbol table is a data structure which is used to store the information about phases, what type of information it stores. Actually, identifiers related information can be stored into symbol table. For example, in this, we are having sum is one identifier, initial is one identifier, value is one identifier. So now in some particular locations, it stores all the identifiers in separate locations. For example, the location one sum, then second location initial, third one is value, like this. Okay, now for any phase, the information regarding these identifiers required, it takes from the symbol table. This is one simple example of symbol. So this is the module that can be accessed by all the phases of the compiler. The information of all the variables, constants, along with type of variable and constants are stored here. That is simply tokens, the token information. This is the one example of symbol table representation. Then coming to the error handler. So what is error handler? Phase wise it encounters errors. Then by invoking some error recovery strategies, those can be handled. So error handler invoked whenever an error is encountered in any of the phase. All the phases are connected to the error handler. Each phase encounters errors. So this routine attempts a correction, that is error correction, so that subsequent statements need not be discarded and many errors can be identified in single compilation. So if you won't rectify the phase-wise errors, then finally whenever you are compiling your program, it is very difficult to trace all the errors. So finally, that's why phase-wise, if you can rectify the errors, wherever error is occurred, then that can be discarded if any error statement by invoking some error recovery strategies, then it is easy to compile your program finally instead of struggling at the end. Okay, now finally the glance, the phases of compiler, whatever I explained here, all the phases at one place are shown in this table. Any example you can take, so you can convert into phase wise. So that is the phases of compiler with detailed explanation about all the phases. So then coming to the lexical analysis or scanner, here quickly we will see the role of the lexical analyzer or scanner. So this diagram shows in the compilation model what is the role of lexical analyzer, how it is connected to the next phase, that is the second phase, parser or syntax analysis. Here you can see for every phase you can keep the compilation block diagram as the base. So whichever the phase we are discussing or studying, take that phase, then what is the next phase, then how it is connected, what is the input and output. Only these things you can keep in your mind. Now we are talking about lexical analysis is the first phase. What is the input of lexical analysis? Source program. Then what is the output of lexical analysis? That we know, token. This is connected to the second phase, parser or syntax analysis. Now the parser or syntax analysis takes input as token, then produces syntax tree that can be connected to the next phase, semantic analysis. So here next phase, no need to draw other phases. Just you can give what is the next phase, that's it. Then commonly symbol table is connected to all the phases. Here you can see lexical analyzer produces output as token. Then token will be considered as input to the parser or syntax analysis. So then that token is represented into hierarchical form, that is partial derivation tree that will be given to the semantic analysis phase. Then again it asks for next token, get next token from the lexical analyzer. Like every token that can be represented in the hierarchical form. Then any information required for the lexical analysis or parser like identifier, constant, etc. that can be stored in the symbol table that can be accessed in both directions. So lexical analysis stores information here. Symbol table gives the information to lexical analysis. Parser stores information on symbol table. Symbol table gives information to the parser like this. Both way communication. So this is the role of the lexical analyzer in the compilation model and how it is connected to the next phase, that is syntax analysis or parser. Okay, now here we discussed about the term tokens, but in addition to token, we are having other definitions also. Why? Because in the lexical analysis, these are all very important. Even some short answers you will get defined token, pattern, lexeme, or for the given source program or input, find what are the tokens, what are the patterns, what are the lexemes. That's why we have to know the definitions and examples. So token we already discussed. So again you can recall once. What is the token? Smallest logically cohesive sequence of characters of interest in the source program. See, smallest logically cohesive sequence of characters of interest. That means all identifiers are one group, all constants are one group, all keywords are into one group, all operators are into one group. So these grouping of sequence of characters are called as tokens. So a lexical token, what is the output of lexical analysis? Token is a sequence of characters that can be treated as a unit in the grammar of the programming languages. A token that can be represented as a pair actually consisting of the token name and an optional attribute value. So like this, so we can represent. So this is a token For example, ID, here value. For example, here ID1, comma X. X is the identifier one. This is the representation of token. So examples of token, for example, type tokens, identifiers, so then number, then real, etc. Then some punctuation type tokens like uppercase if, then some void return, then alphabetic tokens like keywords, then even some other operators also there. Operators also you can consider it as the tokens. Single character operators like equal, plus, minus, all the relational operators, only single character. Multi-character operator, colon equal, double equal, not equal, so then less than or equal, greater than or equal, like, etc. Then again keywords, some if, while, for, etc. Then identifiers with our user-defined identifiers by underscore variable. The name should be in single. If you want to combine multiple strings, you can use underscore. Some flag one, even identifier consisting of starting with letter followed by digits, then repetitions also, my underscore variable, etc. These are all user-defined identifiers. Then some numeric constants are literals like 1, 2, 3, 45.67 with exponential value 8.9 e power, etc. Some character literals within single quotations, suppose A, similarity, then R, etc. Then some string literals, that string can be within double quote, like. These are all some of the examples of tokens. See, by seeing all these, your programming language, any programming language, any program, which is combination of all these type of tokens only. Okay, now there are some non-tokens also. See, let us see some of the examples of non-tokens. So comments are not tokens. These are all non-tokens. Then preprocessor directives also, like has include, has define. These are also not tokens. These are non-tokens. Then some macros, blank, white space, space tab, end of line, new line. These are all not tokens. In any programming language, any of these are all not tokens, which are called as non-tokens. So here you need to identify only tokens in the program. Then coming to the other two terms, patterns and lexemes. So what is a pattern actually? So pattern is nothing but in the given source program, by reading the input character by character, what is its name actually? The description actually. The description. A pattern is a description of the form that the lexemes of a token may take. What is lexeme? The actual values in the given source program are called as lexemes. For example, here x equal to y plus z into 10, x equal y plus z into 10. These are all called as lexemes. Then what is x? What is x actually? This is identifier. The meaning, identifier. Y is also identifier. Z also identifier. Plus is addition operator, equal is assignment operator, into is multiplication operator, 10 is constant. The names, the descriptions of the lexemes are called as patterns. Then what is token? You can represent the token like pair format, the token name comma value. So that is token. Now you can see a pattern is a description of the form that the lexeme of token may take. A pattern is described as a rule describing set of lexemes. For example, examples of patterns. What type of patterns are occurred in any program? That means tokens only. Keywords is one pattern. Identifier is one pattern. Operators also some categories, relational operator, arithmetic operator, etc. Then symbols. These are all some of the types of patterns. Then lexeme means in the given source program, whatever the values from left to right, all are called as lexemes. A lexeme is sequence of characters in the source program. As it is, you can take sequence of characters in the source program that matches the pattern for a token and is identified by Lexical-Analyzer, which is an instance of the token. A lexeme is a string of patterns read from the source file that corresponds to a token. For example, here you can see character, string, the array brackets, whatever each and every thing you have to consider in the given source program, that is called as lexim. Then the description of the lexim is called as pattern. Then the pattern representation by grouping, that is called as token. Now all three at one place. Let us see this example. So source code equal to character string array type equal to hello ended with semicolon. So let us see. Now in this, now you can identify what is pattern, what is lexim, what is token. First to pattern, before pattern, first you can write down lexim as it is. Why? Because from left to right in the given source block, you can separate all characters. So here first we are having CHAR, this is one type, data type, separate type. Then string is one name of that character, whatever we creating, the array string. Then array open bracket, then closed bracket, next equal assignment operator, then literal. In the literal we are having string. So that you can include. We can't separate the quotations, open quote, end quote, and hello. Why? Because this is a literal, can be stated as single string, include as it is, ended with semicolon. Now let us see. So all we have listed. Now you can see 1, 2, 3, 4, 5, 6, 7. Total 7 items are listed. These are all called as lexemes. Now you can describe the names of these lexemes. What is character? This is actually keyword. What is str? This is identifier. What is this bracket? We'll call it as array bracket, left bracket, or sometimes we'll call it open bracket. Then this is array closed bracket, that is right bracket. Then equal, this is operator. Then hello, this is actually literal, the string. Then semicolon symbol. So that description is called as pattern. Now, based on the pattern, you can define the tokens now. The tokens are represented, now you can see the keyword, actually keyword can be represented with the name, character. Actually you can represent like this, CHAR, comma, value. This value is actually optional. Wherever it is required, you can use. This is the token representation. Generally tokens are represented with uppercase letters for discrimination. Then identifier, actually here you can see ID, comma 1. Here two values are there. This is the name of the token, this is the value. Pair, so name, comma value. Then left bracket, so left underscore bracket. Then right bracket, right underscore bracket. Then operator, specify the name of the operator. Actually the token exactly specifies the names. So here what is this operator called? Assignment operator. In short form ASSIG underscore OP. Then this string actually hello, what it exactly name of the token? Literal category. Then the symbol, what is the name of the symbol? Semicolon, semi underscore colon, like this. So any given source string or input, you can identify what are the patterns, what are the lexemes, what are the tokens. First you can list the lexemes as it is in the given source program by separating all. Then you can provide the description of these lexemes, that is pattern. Then you can represent into tokens with specific names. So that is the token, pattern, and lexemes. So this is an important one, even for lexical analysis. Further, by using this, you can represent these tokens into regular expressions. Then regular expression too will construct automata. Then by using automata, we can recognize the tokens, whether these are all valid or invalid, acceptance of the tokens. Okay, now another important concept in lexical analyzer or lexical analysis, we are having automatic lexical analyzer generator, one tool which is called as Lex tool. Sometimes in examination they will ask this question also, explain about the Lex tool or write the Lex program for recognition of tokens, etc. Just briefly we will see about this one. So actually Lex or Flex in the Unix or Linux platform, the tool name is called as Flex software. Automatically it will commit as inbuilt tool. So Lex or Flex, a language for specifying lexical analyzer. This can be implemented by the scientists Lesk and Schmidt at Bell Lab initially for the Unix platform. So not only it is a table generator, but also allows actions to associate with regular expressions. So Lex is most widely used in the Unix community. Then Lex is not efficient enough for production of compilers, however. So some aspect here, so this is good one, especially in the Unix and Linux environment. If you can see the working of Lex tool, so diagrammatically the structure or the role of the Lex tool is represented here. Let us see the diagram. So in the examination compulsory, you have to write this diagram whenever you will get question on Lex tool. So this can be done in the following steps. First, the Lex program that can be written in a language which is called as Lex language. The extension of Lex language is .l. So file name .l. So for example, lex.l, this is the source program. Then that can be compiled by using Lex compiler. In the Unix or Linux, it will comes the default compiler. So we no need to install separate software. So just we have to call the software in the Unix or Linux environment, then using the compilation commands. So you can compile the Lex program. So using Lex compiler, the source language that can be written into Lex language converted into other form. So that form is called as C. Actually, this is C language. So the Lex language is .l is converted into .c. Directly it won't convert into object. Lex language to C language. So the output file name by default it is created like this, lex.yy.c. Okay, now this is the C program actually. Then C program is compiled using C compiler. Now the second step, you can take the C compiler. Input is the C source program, which is the output of Lex compiler, lex.yy.c. Now normal C program, whenever you can compile using C compiler, then it converts into some object file, that is a.out. This is object file. Now this object file is again what it contains. It contains the input stream as the input, and it produces the tokens, sequence of tokens here. Why? Because Lexical-Analyzer generator is part of lexical analysis, that is automatic lexical analysis generation. The output of lexical analysis is token only. So whenever you are using any tool related to lexical analysis, what it produces? Output as tokens only. It won't produce as output as your target program. Why? Because this is only lexical analysis related. This is the use of Lex tool, that is creating a lexical analyzer with Lex tool. Then what is the structure of the Lex program? So Lex program actually it consisting of three parts. So that is first declaration, followed by auxiliary rules, then procedures. It has three parts. The Lex program has the following three forms. First, declaration part within this symbol, double percentage symbol, so you can declare. Then all the constants, whatever the tokens you can define. Then the rules for the tokens that we will call it as translation rules. That is second section. Then any methods are there that you can use, auxiliary functions or methods. So any Lex program consisting of these three parts. The first part, declaration of all the manifest constants and all the tokens, etc. Then the rules for identifiers, whatever, etc. You can define the rules. Then any methods you used, so that methods are used in the translation rules actually. Then the implementation of the methods can be defined in the auxiliary functions. This is the structure of Lex program. Okay, now that's all about Lexical-Analyzer generator tool. Then the role of the lexical analysis, then tokens, patterns, and lexemes, etc. Okay, now we will move to our next phase, that is syntax analysis or parser. This is very important. Why? Because here more problems are occurred in this. Here also let us first recall the role of the parser or syntax analysis. see the diagram, the role of the parser. So in lexical analysis, we already mentioned the similar diagram. So, but here you can consider the parser followed by next right part of the parser or syntax analysis. So up to this same in lexical analysis we discussed. Now after parser, what it contains actually the semantic analysis, intermediate code generation, code optimizer, then code generation. Here all the other pages we will consider it as the rest of front end. So till intermediate representation. Okay now. So output of the parser or syntax analysis, which is parse tree, that is abstract syntax tree. Okay, now that will be considered as the input to the next phase semantic analysis. Then the semantic analysis provides some semantic checks or validations. So by using annotations, then that can be converted into some intermediate representation in the abstract syntax tree or three address code form like that. Further pages will be continued later. Now the role of the parser or position of the parser in the compilation model, here you can see the input of the parser is token, output of the parser is parse tree or abstract syntax tree. Okay, now here also a symbol table is connected. Then what is the role of the parser, which takes the tokens from the lexical analysis and converts the tokens into hierarchical form, which is tree form, which is called as parse tree. Okay, like for every token that can be represented into in the hierarchical form. Then the information about the tokens that can be stored in the symbol table, whichever required. Whenever you are constructing a parse tree, so you want actually what are the variables, what are the constants, so that information that can be taken from the symbol table. Okay, now this is the role of parser in the compilation model or in the phases of compilation. Okay, now what are the types of parsers we are having? So mainly we are having three general types of parsers for a grammar. The first one is called as universal parser. The second one is called as top-down parser. Third one is called as bottom-up parser. That universal parser, that is the basic one that we won't consider. So we'll consider only these two, top-down parser and bottom-up parser. So what are the universal parsers? Universal parsing methods such as like CYK algorithm. So that is Cock, Anger, Kasami. In formal language and automata theory course in our previous semester you studied, we are having the membership algorithm of context-free grammar, CFG membership algorithm one that is CYK. So here this will be considered as a universal parser. And some early algorithm which can parse any grammar. These general methods are however too inefficient to use in production of compilers. That's why we can't use here. We'll concentrate on the top-down and bottom-up parser. Now, what are the top-down and bottom-up parsers? The methods commonly used in compiler can be classified as being either top-down parser or bottom-up parser. So, top-down parser, construction of the parse tree starting from the root and proceeding towards its children. So this is the top root, then bottom what it contains children. This is called as top-down parser. Whereas bottom-up parser reverse. Bottom-up parser will take children, means here we'll take the string. Then we will derive its root. Here you can see this is bottom-up parser. So in the derivation, top-down parsing means we'll take root and derive its children means string. Here you can derive string. Whereas bottom-up parsing means reverse substitution. You can take the string, then derive root. Root means starting variable, the grammar. This is a simple representation of top-down parsing and bottom-up parsing. So as implied by the names, top-down method build parse tree from top root to bottom, that is the leaves, while bottom-up parser starts from the leaves and work their way to derive its root. So in either case, the input to the parser is scanned from left to right only, one symbol at a time. So these are all top-down and bottom-up parsers. Now let us see what are the techniques of top-down and bottom-up parsers. parsing techniques. This is a very important topic. In the entire of second unit, we are having total 3 plus 2, 5 problems. Definitely you will get 2 questions. Why? Because you are having internal choice. Unit wise, 2 questions will be given. 1 question you have to answer, either first part or second part. Like all units you have to prepare. There is no choice, overall choice. You are having unit wise choice only. Now for top-down parser, what are the various techniques we are having? In top-down parser, we are having recursive descent parser with the backtracking. This is very simple. We can define recursive procedures for each and every grammar symbol. Then recursive descent parser with no backtracking. Then that is called as predictive parser. This is very, very important. Predictive parser. Definitely you will get this question. So in the predictive parser, we are having LL parser also. Once you know the predictive parser, just for one rule, you can define is it LL parser or not. Then coming to bottom-up parser, in bottom-up parser, we are having LR parsing. So in LR parsing, we are having 3 techniques. One is simple LR, it is called as SLR. Then second one is called as CLR, canonical LR, CLR. Then third one, look ahead LR, LALR. So these 2 are powerful LR parsers actually. Powerful LR parsers. In our syllabus, see, they have mentioned powerful LR parsers means LALR, CLR. Then simple LR means the basic one. Okay, now for all these 3 LR parsers, the common things you needs to be followed. Common factors for all LR parsers. Model is same. Then parsing algorithm is same. These 2 are common. Then where these are all differ? Parser to parser, parsing table is differ. Only parsing table. Parsing table is differ. But the model one, suppose in examination, you will get any question, explain SLR parsing model, explain LALR parsing model, explain CLR parsing model, and explain the parsing algorithm of SLR, parsing algorithm of LALR, parsing algorithm of CLR. The common LR parsing algorithm only you can explain, but you can make the name as if it is SLR or CLR, LR. That is the only. But everything is same. Model also same. Only parsing table is differ from parser to parser. Now here we will focus on how to construct predictive parser followed by LL parser. Then the 3 parsers. 3 plus 1, 4 problems we will discuss now. Briefly one by one. Okay, now before that here, for the parser, context-free grammar plays major role. Just see the glance of context-free grammar. Even in formal language automata theory also you studied the CFG concept. That is for type. For which type this grammar comes? We are having type 0, type 1, type 2, type 3. This is regular language, normal grammar. This is context-free language, context-free grammar. Then type 1, context-sensitive language, context-sensitive grammar. Then type 0, this is phrase structured or unrestricted grammar. The language is called as recursively enumerable. Okay, now where you studied context-free grammar in type 2. C. See the tuple definition, VTSP. V set of variables, T terminals, S starting variable, production. P set of production. The productions are of the form alpha derives beta, whereas alpha belongs to V, single variable, beta belongs to V union T, string of variables or terminals including null also. These are all the production rules of context-free grammar. Again here reviewed the same here. For example here, one conditional statement that can be represented in the form of grammar statement equal to if condition statement else statement actually. If condition statement 1 else statement 2. This can be represented in the form of grammar. Statement equal to, that is represented with arrow, derives. If the condition can be represented within parentheses, here the expression condition. Then statement 1 stmt, else statement 2. So this is one grammar. Example of grammar. Okay, now here in our compiler design, even in semantic analysis also, we will use one standard grammar, that is arithmetic expression grammar. Recently, we have constructed the parsed E derives E plus E, E minus E, E into E. That is the standard grammar used here. This is the definition, what I explained here. Just review once, because you always studied in formal language and automata theory. Again, in syntax analysis, it is very important. So then, this is the arithmetic expression grammar. The same is given here. But for problems here, directly expression we will use capital E, term we will use capital T, then factor we will use capital F. Now, by converting this, let us see what is this one. E derives E plus T, the first production. Then the second production, E derives E minus T. Then third one, E derives T. Then fourth one, T derives T into F. Then next one, T derives T by F. Then next one, T derives F. The next one, F derives expression within parentheses. The next one, F derives identifier. In this, you can see in the grammar, G equal to VTSP, just identify what are the variables here. Here the variables are capital E, T, F, expression, term, factor. Then the terminals are all the operators and boldface characters also. We are having plus, minus, into, divide, left parenthesis, right parenthesis, ID. This ID is boldface character. So these are all terminals. Then what is the starting variable in whatever the first production, left hand side, whatever the variable, that is the starting variable. So E is the starting variable, S equal to E. So then the productions are, these are all the productions. So like in the given grammar, we have to know what are the identifiers, I mean, what are the variables, what are the terminals, then what is the starting variable, you need to identify. Then the productions. So any grammar, it contains only one starting variable only one starting variable. Then the notations, all the terminals are denoted with lowercase letters, then operator symbols, some punctuations, parentheses, comma, etc. Then digits 0 to 9, then boldface characters, ID, if, etc. Then non-terminals or variables are represented with uppercase letters, capital A to capital Z. Then using some italic names, lowercase strings like expression statement. Then using some special Greek letters also, alpha, beta, gamma, etc. These are all some notational conventions used for variables and terminals. These are the various notationals are given. Even Greek letters also used for the variables. Then all the productions in the form of alpha derives beta. Alpha left hand side, it contains only single variable. Right hand side, it contains a variable followed by terminal or only variable or only terminal including null also. So this is the grammar what I explained here in simplified form, arithmetic. Okay, now whenever we are moving to top-down parser, first there are some drawbacks or difficulties in top-down parser. So we have to overcome all these difficulties whenever you are implementing the top-down parser. So the first difficulty in top-down parser, ambiguity. So what is ambiguity in context-free grammar? How can you define ambiguity? For at least one string, if there exist two leftmost derivations or two rightmost derivations, or two derivation trees or parse trees for at least one string, then the grammar is said to be ambiguous grammar. So then how to eliminate ambiguity also you are having in the portion you already studied. So using disambiguity rule in case of if then else grammar. Then in case of arithmetic expression grammar, using precedence and associativity of operators. These two methods which are used to eliminate ambiguity. That is one difficulty. Then another one, left recursion. So if any grammar is left recursive which is not suitable for top-down parser, you have to remove left recursion. This is one important concept. How to remove left recursion? One example problem I will explain. Then any grammar having ambiguity not suitable for top-down parser, remove ambiguity. Then non-left factored grammar. So that means left factoring is must for top-down parser. So how to remove the left factor? That means in the right-hand side of the production, wherever the common values are there, prefixes starting right-hand side, leftmost, more than one production having common prefix, those can be taken as factoring out. So then that can be now non-left factored grammar is converted into left factoring. So this is very important in top-down parser. Then backtracking. So backtracking is also necessary for top-down parser. Suppose in one production you substituted for deriving your string. So in that way your string is not derived. At that time you can go back and check is there any alternative substitution for the same variable. So at that time you can go back and substitute alternative production. That going back is backtracking actually. So without backtracking, every time we can't get our required strings. So backtracking parsers are more powerful than predictive parsers. They are also much slower, requires more time. Therefore, backtracking parsers are not suitable for practical compilers. These are the difficulties in top-down parser. Now, whenever if you want to construct predictive parser, the grammar should satisfy all these. That means grammar does not contain ambiguity, grammar doesn't have left recursion, grammar should be left factored. So all should be satisfied. Then only you can start constructing predictive parser. Now let us see the elimination of left recursion. Sometimes in examination you will get one question. For the given grammar, eliminate the left recursion like this. It's an important concept. So a grammar G is said to be left recursive if it has a non-terminal A such that there is a derivation is of the form. A derives A alpha. Here why you use it plus? So compulsory one or more productions are used to derive this one. Where alpha is string of terminals and non-terminals. If you can draw its derivation tree for this, for example, your production is A derives A alpha actually. If you can draw its derivation tree, this is the root. Right hand side you can connect A, alpha. All the symbols in the right hand side, left to right you can connect. Again, A you are having substitution. What you are having again? A alpha. Again A you are having A alpha. Again you are having A alpha. Here you can see this is the root. Left side you can see the leftmost the same variable is repeated. This is called actually immediate left recursion. This is called as immediate left recursion. The left hand side variable and the right hand side leftmost variable should be same. If any grammar is like this, then you can say it is in the form of left recursion. This is not allowed in the top-down parser. We have to remove this. So how to remove this? Let us see. You are having indirect left recursion also. By substituting some productions, at that time you may get left recursion. That is indirect left recursion. So the grammar may having immediate left recursion, the previous diagram what we discussed. Then indirect left recursion. During the process of derivation, you may get this one. That is indirect left recursion. So, but our concentration is on only immediate left recursion. The given original grammar immediately, whenever there is left recursion, you have to remove. See what I explained. A derives alpha, the diagrammatic representations. This is immediate left recursion. For example, here consider this grammar. Here you can identify which are the productions having this left recursion. Here E derives E plus T or T. At least any one in the right hand side having the prefix same as left hand side variable. These two are same. So it has left recursion. And T derives T into F or F. Here TT, so it is same. It has left recursion. But F derives, it is starting with parenthesis. So, but indirect left recursion is there. But here our concentration only on immediate. So here no left recursion. Production wise, you have to check. In the given grammar, production wise, you have to check whichever the production having left recursion. So you have to eliminate the left recursion. Then how to eliminate left recursion for these two? So as per the procedure, we are having some rules for elimination of left recursion. So let us see the rules here. See the above example diagrammatically represented here. You can see E derives E plus T, E, immediate left recursion is there. T derives T into F, T, T. So immediate left recursion is there. Now F derives E within parentheses, we are not having immediate left recursion. That is indirect left recursion. Okay, now what are the rules for elimination of left recursion? We will see. Only immediate left recursion we will eliminate here. Now you can see. If any grammar is in the form, this is the general form of left recursion grammar. A derives A alpha or beta. Here capital A is the variable, alpha and beta are string of variables or terminals, whatever. But only our intention is left hand side starting variable, right hand side leftmost, anyone matching with left hand side, then it has left recursion. Then whatever the alpha beta values, you don't bother about. But here beta does not start with the variable A. Why? Because already here A alpha is there. If you are having one more variable starting with A, that comes under this one only. A alpha 1 or A alpha 2 and so on like this. For n productions, beta does not start with A. This grammar has left recursion. Now how to eliminate the left recursion for this? So again you can see the general for n productions are there, how the left recursive grammar will be. Before that, first let us see whenever you can apply the derivation. First we have taken A derives beta. So here only the string beta only derived. Further what beta we don't know. Then if you can take A alpha, first production, A we are having substitution. A we are having, what are the possibilities? You may substitute again A alpha or beta. Suppose if you can substitute beta alpha, here you will get the string beta alpha. Next time A alpha, A is substituted again A alpha. Next A is substituted beta, beta alpha alpha, the string. Next time, for example, repeated A alpha n times, last beta is substituted and so on. So these are all the strings you will get here for this left recursive grammar. Like this, if you are having n productions which are in the form of left recursive form, that also we will see. First, for these two, what are the rules for elimination of left recursion? So the language is like this. Every time it is start with beta followed by alpha I greater than or equal to 0. So now you can write the productions like this. A derives beta A dash. A dash should be 0 or more alphas here. Here this alpha is substituted with A dash. Okay, now what is A dash? What A dash contains? It may contains null or alpha followed by A dash may be repeated. Now you can see A derives A alpha, the equivalent productions after eliminating left recursion. The first rule is A derives beta A dash. Then what is A dash derives alpha epsilon or alpha A dash. These are all the two rules actually. So any grammar is in this form, you can apply these two rules for elimination of left recursion. Okay, now A derives beta A dash, then A dash derives alpha A dash or null. These two rules you can remember. If any production is in the form of A derives A alpha or beta, non-left recursive grammar rules, A derives start with beta, then new variable A dash is introduced. Now what is A dash? It is null or alpha A dash. These two rules. Now you can see here A derives beta A dash. There are no left recursion. A dash is null, then A dash derives alpha. No left recursion. This is non-left recursive grammar. You may consider it as formula. For any grammar is in this form. These two rules you can apply. Then that grammar is converted into non-left recursive format. Like this, if you are having n productions, this is see if you are having n productions in general, A derives A alpha 1, A alpha 2, or A alpha 3, and so on A alpha n. Here A is common. The prefix is repeated every time. Same with left side. Then followed by alpha 1, alpha 2, whatever the value. Or next beta value, 1 or beta 2, and so on beta n. Here you can see beta does not start with A. So in this, the general form what we used to A derives A alpha or beta. The first rule A derives beta A dash. Second rule A dash derives epsilon alpha A dash. Substitute these values as for rule 1. This one. A derives beta A dash means beta 1 A dash or beta 2 A dash or beta 3 A dash and beta M A dash. Why? Because beta is repeated M times. Similarly, next rule A dash derives null or alpha A dash. We are having alpha repeated n times. Alpha 1 A dash or alpha 2 A dash and so on alpha n A dash. This you can make it as formula substitute any connection with any number of. Okay, now take an example of recursion. Here you can see it has left recursion. It also having only you can take the left recursion production. E derives E plus T or T. It is in the form of A derives A after A whatever that is alpha or now beta. Beta equal to T, alpha equal to plus T, then capital A equal to E here. The rule 1 A derives beta A dash, then A dash derives alpha A dash or null. So using rule 1 you can substitute this one. So what you will get this one. So here A means E derives, beta means T. Now A dash means here E dash. Now next one A dash equal to means T dash using rule 2. E dash derives alpha. Alpha means plus T. So then plus T dash. After left recursion, here you can see E derives T dash, E dash derives plus T dash or lambda epsilon. Then similarly T derives T into F. Here you can see same. T derives Ft dash, then T dash derives star Ft dash or null. But F derives E within parenthesis ID no left recursion. Now this is the grammar after removing left recursion. Production 1, 2, 3, 4, then 5. Total the 5 productions. So like this, any given grammar, we can remove the left recursion. So that is the example problem. Okay, then coming to our predictive parser, why we discussed left recursion means for predictive parser is the prerequisite. Predictive parser is also called as recursive descent parser without backtracking or non-recursive descent parser. So we'll see predictive parser. So for predictive parser, whatever the difficulties in top-down parser, any grammar that doesn't allows all. That means we have to remove ambiguity, we have to remove left recursion, then non-left factoring, etc. All needs to be addressed. So you can see the model of the predictive parser. So sometimes theoretically you will get question. Explain the predictive parser with the block diagram or working of predictive parser, etc. This is the diagram. The model of predictive parser mainly it consisting of the components. Predictive parsing program is the main component. What it contains: output component, parsing table component, then it contains input or input buffer, then it contains stack also. So what input or input buffer contains the input or the source program is stored or the string is stored in input buffer ended with an end marker. So dollar, we will call it as dollar is the end marker. Now the string is stored in the tape, one symbol in one cell only, like A1, A2, and so on, AN. Then what stack contains? Initially, it contains the end marker, that is the empty of the stack, empty symbol of the stack, then some grammar symbols X, Y, Z. So always the predictive parser sees the top of the stack and the current input symbol, these two. Based on this, actions are defined. Actions. So top of the stack and current input symbol. Then it produces output accordingly. What is the output here? Parsing done successfully or not. The output is parsing successful, parsing not successful. So how this will be done, these actions, by constructing the predictive parsing table. Now here our problem is how to construct this table. That is the important question. Construction of table, predictive parsing table. This is the complete model of predictive parser. So briefly, let us see the description of all the components. I already explained, the same only given here. So the input or input buffer contains the string to be parsed on the input string, ends with a dollar, where dollar indicates end of the input. And stack contains sequence of grammar symbols, and dollar is placed initially on the top of the stack. When dollar is on top of the stack, then what indicates stack is empty. Normally in our data structures, we may call it as Z or Z0. So here dollar is used. The meaning is same, whatever the symbol. So whenever the empty symbol that should be on top, then it indicates the stack is empty. Then another important component, parsing table, which is a two-dimensional array denoted with M of A, comma A. So here, where M is, we'll call it as the model, parsing model. So here, two-dimensional array, first it contains the grammar variable followed by a terminal or dollar also. Here you can see the entry also, it will be like this. So all the columns are terminals plus dollar, then all the rows grammar variables. So M of A, comma A. Here this is A, here capital A. The entry variable A on terminal A. What is this value? The entries in the table are combination of the productions only. Then if any entry is blank, so that indicates error. So this is the structure of predictive parsing table. Then how to construct this table, that is our problem. Then parser program. What is the role of parser program? Which takes different actions based on X, which is the symbol on top of the stack, and current input symbol. So here X is the stack top symbol, A is the current input on input buffer. Based on this, the actions. The actions means whether you have to simplify or move. Then finally, our string is derived. Then you can say parsing is completed or not. As the output, the productions that are used are displayed, using which the parse tree can be constructed. Like in parse tree, whatever the productions we will use to derive a string in top-down parsing, starting with root here also. So finally, our string is derived. Then you can say the parsing is successfully. Suppose your string is not derived, you can say the parsing is not successful, like that. The same scenario here also will use. But automatically, whenever you can implement this predictive parser using this algorithm, so it performs. Okay, now for construction of predictive parsing table, the two prerequisite values are required: first values and follow values. So even in examination, sometimes you will get question for the given grammar, find first and follow values as a 2 mark questions, or even long answer part A or part B, something like. Or write the algorithm or rules for calculation of first and follow values. So these are all very important. For predictive parser, with this only we will construct. So the predictive parser can be easily constructed once we know first and follow sets. These are not single values actually. More values are there. That's why we'll call it as sets. So these sets of symbols help us to construct a predictive parsing table very easily. Okay, now let us see how to construct this with examples. Briefly we will explain. Then followed by how to construct the predictive parsing table. Once you know these values, easily you can construct the predictive parsing table using the algorithm. Now you can see the first value is very easy. How to compute first value? So even for first and follow, we are having certain rules. Simply by following the rules, easily you can construct. First, how to compute first values? If you can see the definition of first. For example, first of alpha is defined as set of terminals that appear in the beginning of the derivation derived from alpha. Suppose alpha derives something. In the derivation, beginning of the derivation, any terminal is there. That terminal or set of terminals are called as first values. Formally, let us say this can be defined as shown below. First of alpha equal to. Suppose if alpha equal to null. Here you can see by default null is there means first of null equal to null only. Then alpha derives null also using derivation. So directly, for example, alpha derives null. Then what is first of alpha? Null. Then alpha derives null by substituting. You are getting null. So again, the first of alpha is null only. Then if you are having derivation like this, alpha derives terminal A beta. In the derivation beginning, this is the beginning. Beginning what you are having a terminal A. Now A is first of alpha like this. So the first values are combination of terminals including null also. In the direct production, if you are having a terminal in the right hand side of the beginning, take the terminal. Or directly null, you can take the null as the first value. So, but you don't have direct terminal, direct null, but you are having substitutions. After substitution, you may get in the derivation is of the form terminal followed by something. At the beginning, terminal means directly you can take terminal as the first value. That is the definition here. Okay, now let us see the one example followed by what are the various rules for computing first value. For example, the grammar is like this. See, the first sets for each non-terminal in the following grammar we need to compute. In the left-hand side of the production, whatever the variable or non-terminals, for those we have to construct first values. So E derives T dash, we have to compute here first of E, the left-hand side one. That depends on the right-hand side production. Here E dash derives plus T dash or null. We have to compute here first of the variable E dash, this one. T derives FT dash. Here you have to compute first of T. Then here T dash derives star FT dash or null. Here you have to compute first of T dash. Here F derives E within parenthesis or ID. Compute first of F. So here, by using right hand side productions, if directly you are having terminal value, you can take directly those values. If not a terminal, if you are having variable, then again you can find first of those variables in the derivation like that. Here E derives T dash. Directly you don't have terminal. First you need to find out first of T. Then whenever if you want first of T coming to T derives FT dash, you need to find out first of F. Again coming to F, first of F you can find from this. Here you can see here this is the production. You are having terminal. In the beginning we are having terminal left parenthesis, or you are having a terminal ID. ID is also terminal. So here first we can find easily first of F equal to, actually this you can write first of left parenthesis E right parenthesis. The first one only you are having only terminal at the beginning, only take the first terminal only. If you are having two terminals also, only first terminal you can consider. So this is the first value. So here you will get first of left parenthesis equal to left parenthesis. Then another production you are having first of ID. ID is a terminal. So first of ID equal to ID only. Now combine all these. Therefore, first of F equal to left parenthesis comma ID. These are all first values. So once you know the first values, now here first of E we are finding this one. E equal to substitute what is the production? First of TE dash. Now first of TE dash means first of T. This is equal to first of T. Now what is first of T? T derives FT dash. This is equal to first of FT dash. Again first of FT dash means first of F you can find out. First of F equal to, here already we calculated, left parenthesis comma ID. Therefore first of E equal to left parenthesis comma ID. First of E once you know, then first of T also same. First of T is also left parenthesis comma ID. Once you know first of T, then first of F already we calculated. So now first of E, first of T, first of F, all three are same. Left parenthesis comma ID. This is equal to left parenthesis comma ID. First of T is also left parenthesis comma ID. Then first of F equal to left parenthesis comma ID. Okay, now E, T, F values are calculated. Then coming to E dash. So E dash derives plus T dash, already starting with terminal. So first of terminal followed by anything. Terminal only you can take. This is the first value. First of null equal to null. Therefore, first of E dash what you will get? Plus comma null. Then similarly, first of T dash star FT dash. Star is terminal, directly terminal or direct null. First of T dash equal to star comma null. Now you can see first of E, first of E dash, first of T, first of T dash, first directly we calculated. So, but we are having rules here to calculate all this. So, suppose in the right hand side, all variables derives null. At that time, how to compute first value? Or after substituting a variable by null, how to calculate? Like all this comes under the rules. So whatever I explained, the same is shown here. Then directly we'll move to the rules for computing all the first values. This is the table, the final first values for all the variables or non-terminals. In the algorithm, you will get all the possible rules for finding first values. In examination, sometimes they will ask this algorithm also. Are rules for computing first value. All these rules you have to write. So to compute first of x, x is the grammar symbol variable. Applying the following rules until no more terminals are null can be added to any first set value. Rule 1, if the production is of this form, x derives a alpha is a production. Here right hand side small a is a terminal. Then first of x equal to directly terminal you can take. Direct terminal value. That is rule 1, very simple. If any production starting with terminal in the right hand side or null, the null is in the second rule. X derives null is a production. Then directly this null is added to first of x. Therefore, add epsilon to first of x. First rules are very simple. Right hand side direct a terminal that is added to first. Right hand side direct null value, that value is added to first of x. So if it is not the rule 1 and 2 form, the productions are of the form like this. You can see the rule 3. Rule 3, same, the production is of the form x derives y1, y2 and so on yn. Here y1 to yn are the grammar variables. Directly no terminals are there. Is a production. Let us assume the right hand side all y1 to yn derives a null. Here you can see. Then what you have to do? Suppose here y1 derives null, next y2 derives null, and so on yn derives null. Right hand side all the variables contains a null production. Then what you have to do? You can add whatever the variable you are finding, if it is first of y1, first of y2 and so on first of yn. Suppose first of y1 and so on first of yn. So it is having some plus comma null. First of y1. Then what is the left hand side first of x? First of x equal to first of y1 minus null. epsilon values, first value should be added to first of x here. So now here you will get only plus is the first of x. The same here you can see. X derives y1 to yn is a production. Then if y1 to yn and so on derives null, that means either any one contains null. Whenever you are finding first of its value, if y1 contains null, that means derives null. But y1 contains other than null also as the first value. Then non-null values, non-null first values of y1 can be added to first of x. Then first of x equal to non-epsilon symbols in first of yi. Anyway, examples also we will see. Then you will get clarity. That is rule 3. Whereas in rule 4, almost similar, but entire right hand side is null. Here you can see the rule is written similar fashion, but entire right hand side null. Then what is the first of x? Also null. X derives y1 to yn is a production. Entire right hand side derives null. Means y1 null, y2 null, and so on, yi minus 1 all are null. Then entire right hand side value is null. That is x derives null.
In rule 3, sir.
Yeah, tell me.
In rule 3, entire right hand side is also null, no, sir?
No. Actually, that is the derivation actually. So if any one is null, for example, see, y1 is null, then you have to consider y2. Suppose y2 is not null. At that time, non-epsilon symbols of first of y2 you can add. That is the intention actually.
If any non-terminal exists in right hand side.
Right hand side, see, for example, y1 is not null. Let us assume. So y1 contains direct terminal. So then direct terminal is added to first of x like previous rule. Suppose y1 also contains null. Means the production like this y derives null. Now you can substitute y as null. Then what you will get? This will be eliminated. Then coming to y2. Then we will come to y2 variable actually. If y2 contains null or a terminal, so other than null you can add 2x like this. Not all. If first one null, then go for second one. If second one not null, then directly take this value. If first one not null, directly take first variable, first values only like this. Anyway, in the example I have given clearly, you will know. Whereas rule 4, complete right hand side is null. But in the production I have written similar, but the intention is like this here. All are not null. If any one, the right hand side. If first one is null, then second one we have to consider. Second is null, third one we have to consider. At that time, non-epsilon symbols needs to be added like this. Whereas rule 4, it is not like all the variables in the right hand side are null. Complete you will get null value. Then null is added to first of x. That is like rule 2. Rule 2 what you are having? X derives null. Then null is in first of x like this. Then rule 5, direct terminal or null value. For example, you are having first of terminal, first of null. Direct value only you can take. Terminal only, null only like this. Anyway, now rule wise, let us see the examples. I will get more clarity. If right hand side, if any variable derives null, then only you can go for rule 3 and rule 4. Otherwise, by using rule 1 and 2 directly you can find. For example, rule 1, let us see what is rule 1. The productions are in the form of A derives terminal followed by any. So starting right hand side terminal means direct terminal is the first value. First of terminal A, BC. Direct terminal is there. First of A equal to terminal A. E derives plus T dash. Plus is direct terminal. Now plus is the first of E value. Then A derives terminal A. 3 terminals are there. But here you can consider only starting terminal only. Don't consider second, third terminals. Only starting terminal. First of A equal to small a only. That is rule 1. Similarly, rule 2. When you can use rule 2, only direct null value is there. If any production contains epsilon, right hand side directly. Now you can see is applied only for epsilon productions. A derives epsilon. Direct epsilon is the first of A. Then E dash derives epsilon. Epsilon is the first of E dash. So rule 1 and rule 2. Rule 1 is only for terminal in the right hand side. Then rule 2, only epsilon in the right hand side. If more than one terminal is there in the right hand side, only first terminal needs to be considered. Now let us see the rule 3. The rule 3 is applied for all the productions not considered in the above 2 steps. The production is like this. Now you can check. S derives variable A, variable B, variable C, followed by terminal. So if capital A, first value you can find out. Directly you are having non-epsilon first values. Then you can add to first of S. But if first of A contains null, at that time, what will happen? Let us see here. Then you can consider the second variable also. Now A productions contains null followed by plus B. B productions contains null followed by into B. C productions contains null percentage B. So for this, directly using rule 1 and 2 you can find out. By rule 1, first of A equal to, you will get plus only. Why? Because it's starting terminal. Then for rule 2, first of null, first of A equal to null only. By combining these two, plus comma null. These are all first of A values. Similarly, first of B equal to, by rule 2, rule 1 into, by rule 2 null. Then first of C equal to, by rule 1 percentage, comma, by rule 2 null. Okay, this ABC directly we obtained using rule 1 and 2. But the starting production is not in the form of rule 1 and 2. These are all in the form of rule 3 actually. First, what you have to do? First of A, you can see what is first of A actually? Plus comma null. So here it contains plus comma null, and also A derives null. At that time, non-epsilon first values should be added to first of S. So here you will get first of S equal to first of A minus null. Now what you will get? First of A actually plus null. You will get plus only. Why you have to consider this one? Actually, A contains null production. Suppose if A does not contain null production, this is not there. Then first of A equal to only plus. At that time, directly first of A equal to you will get plus only. So whenever A contains null, then you have to continue with B also. Why? Because whenever put A as null, then your starting variable is B here. Then coming to B. So what is first of B actually? Into comma null. So and also B derives null. So that's why first of S equal to first of B minus null. Now star will be added. If B does not contain null, let us assume only star B is there. This is not there. Then first of S equal to first of star only. If B contains null, we substitute null. Now you will get AB or null. Next variable is C. Now you can continue with C. First of C equal to null comma percentage. So why? Because C derives null. Non-epsilon symbols, that is percentage, is added to first of S. If first of C not contains null, then only percentage will come. Then we can't proceed with the next symbol. But C also derives null. If you will substitute A, B, C as null, now here what you will get? S derives only terminal D. By rule 1, D is also first of S. In this case, first of S equal to what you will get? Plus into percentage D. All values comes under first of S, like this. Suppose here, next rule 4, right hand side all are null. That means here D is not there, A, B, C. Now all are null. Now means right hand side compulsory S derives null. Then this also added to first of S. Along with plus into percentage, null is also added. That is rule 4. Now you will get clarity, the difference between rule 3 and rule 4. So,
Sir, now according to rule 3,
yeah,
first of S is plus star percentage and D and
Yeah.
epsilon, no sir?
epsilon won't come here. Why? Because S right hand side completely does not contain null. Here D terminal is there. It is not null. Even by keeping ABC null, D remains same. So right hand side you
Okay.
won't get null.
Now first of S is first of D, sir.
First of S equal to first case, first of A minus epsilon, then first of B minus epsilon, first of C minus epsilon, then first of terminal. All the four we have to consider.
Okay.
So clear?
What is the final answer, sir?
Final answer plus comma into comma percentage comma terminal D. According to rule 3, first of S.
Okay, sir.
Now rule 4, now you can see. You will get null also. Let us see the rule 4 example. Here you can see step by step whatever I explained. The same is shown here. So first, here you can see. First we have considered first variable. So A contains null production. That's why non-epsilon symbols of first of A added to first of S. First of S equal to first of A minus null. Here plus is added. A, suppose now here S derives A, B, C, D. This is production. Now you can substitute A derives null here. What will happen? S derives B, C, D. So this is removed. Now B is the first. That's why. Again, after substituting B as null, what you will get? First of C, D. Next, we are having null production for C. By substituting C as null, you will get a D like this. By combining all this, you will get all these values. Even a small d is not there. Right hand side, only up to ABC. Now all are null. Then epsilon is also added here. That is, if A is null. Now second case, here A derives null. Then we are coming to the variable B. If A derives null, add non-epsilon symbols of first of B. This one, red one, to first of S equal to first of B minus null. Then B derives null. Why? Because we are having null production for B. Substitute B as null. Then both A, B are null. Then we will come to the variable C. Actually, this is the intention. A, B derives null. First to second derives null. Null is substituted. Then your starting variable is C here. So first of C, non-epsilon symbols you can add to first of S. Now C is also derives null. That means Y1, Y2, Y3 derives null. Now first of ABC means that is null. After 3 null, what you are having? D you are having. Now you can see here ABC are null. By keeping all are null, you are having terminal D. The non-epsilon symbols are first of D. Anyway, this is direct terminal by rule 1. So D is added. Now finally, what are the first values of S? By considering all the cases, plus into percentage terminal D. Here you can see. These are all the first of S values. Then coming to rule 4, almost same. Right hand side all are null. So the production consider like this. We didn't consider terminal here. S derives ABC, the same example. Now A derives null, B derives null, C derives null. Here you can see. Same as rule 3, it will come first. S derives ABC. From here, first of A minus epsilon will be added. From here, first of B minus epsilon is added. From here, first of C minus epsilon is added. By rule 3, this. Then rule 4 is also applicable. Why? Because here ABC both derives null. Here see A derives null, B derives null, C derives null. Right hand side completely null. Here null is means first of S equal to null. This is by rule 4. Remaining are by rule 3. So therefore here first of S equal to plus comma into comma percentage comma null also. That is the only difference. Right hand side if all contains null. The same is shown here. Same as rule 3, only the last step, right hand side if all are null. This is first of A. If A derives null, so non-epsilon symbols of first of A is added to first of S. Then here, whenever A contains epsilon, then coming to B, non-epsilon symbols of first of B added to first of S. Then take two combination. AB derives null. AB derives null means then your next variable is C. First of C, non-epsilon symbols added to first of S. Then next case, ABC derives null. All three variables null. Then what you are having right hand side, only null value is there. Then add epsilon to first of S. Only this is the rule 4. Remaining all are rule 3 only. Now by combining all, you will get all the first values. So like that you can find out the first values. Then rule 5, that is direct. If it is a terminal, first of terminal equal to terminal. For example, plus is a terminal, first of plus plus. Small a is a terminal, first of a equal to a. ID is a terminal, first of ID equal to ID. Direct terminal. This is the computation of first set values. Then coming to follow. The follow is somewhat difficult and you may get confusion also. So carefully you have to follow. So follow, we are having some certain rules here also, but follow value can be calculated the variable that should be occurred in the right hand side. First value means the variable that occurred in the left hand side of the production. For that variable, first value is calculated, but follow value is not like that. In the right hand side, in the sentential form, wherever variable is there, after the variable, whatever the values followed, but that follow value should be terminals only, not variable values. Your first values also only terminal values, combinations. The follow of, for example, variable A. A is the non-terminal or variable. Is defined as set of terminals, small a, that will appear immediately to the right of A, right of the variable in some sentential form. That means in the right hand side somewhere. So that is the set of terminals A such that there exists a derivation is of the form. This is the derivation. S derives alpha variable A, terminal A, beta. Now for this we can find out follow. Follow of A equal to, after A, whatever the terminal. So this is the follow value actually. But directly we can't write, we are having some rules here. Okay, now here alpha, beta, some values, any values. We are concentrating only A. In the right hand side where A is occurred, after A what is there? If it is terminal or something null, based on that the follow of A values are calculated. Suppose A is occurred in the last symbol of the sentential form. That means here A is occurred, right hand side. After A actually what is there here? Null actually. So in this case, dollar by default dollar is in follow of A, where the symbol dollar is treated as the end marker. For example, S derives alpha A beta capital A. So after A nothing is there. So now here follow of A, the end marker will be added by default dollar. So this is the definition of follow value. So here directly after follow of a variable, whatever the value, we can't add. We are having the rules here. Strictly we have to follow the rules here. So according to rule, so we can write the follow values. Now,
Sir, one doubt, sir.
yeah.
If we take the same expression, S tends to
Okay.
above one, sir, which you written.
Yeah.
S tends to alpha A beta capital A. In that expression, if first of A means, what is the answer, sir?
First of A. See here directly you can't
Yes,
find
if
A.
there is no other productions means only that is the production, then at that case, what is the first of A?
Can you tell what is the production now? S derives alpha A beta.
Same.
This one, na?
No, sir, same. No. Alpha A beta capital A.
A.
Yes, same production.
So you want this value.
Yes, first of A.
What is A?
There is no further productions to A. Yes.
Then we can't find first value. Why? Because no productions. If A contains something, then only from this you can find first value.
Okay. In this case, first of A is nothing, sir.
Yeah, first of A is undefined because there are no productions for A. Compulsory first value means
Okay, sir.
it contains a production for that variable. Based on that only you can find. But follow value you can find. After A, nothing is there. Na,
In
even
that case, we can't write epsilon, sir.
yeah.
In that undefined case, we can't write epsilon as answer.
No. For first, we don't have that chance.
Okay, sir.
A contains self-production. Why? Because in the first rules, the 5 rules you can see. Do you have any such case?
No, sir.
So that's why we can't use that. But follow it is possible. Now let
Okay,
us see the rules for follow. So these rules also called as algorithm for computing follow values. So the first rule. So all of you, before doing any problem, whatever the procedure rules, you have to follow those. You have to remember and practice. Then only you can start doing the problem. The first one, in our given grammar, if you are having a starting variable, let us assume S is the starting variable. S derives something. S is the start symbol. Then follow of S equal to dollar is added by default rule. Rule 1. Suppose in our grammar E derives E plus T or T derives T into F or something. Here E, the first production, S equal to E here. Then follow of E equal to dollar. Default, this value will be added according to rule 1. Follow of S equal to dollar if S is the start symbol. That is follow of S equal to dollar. Then the second rule, if the production is of the form A derives alpha, a variable B, beta is a production. Beta not equal to null. Beta contains something. So then you need to find out follow of B. So follow values is not like first value. First value you can find only for left hand side variables using the right hand side production. But follow value directly we can't find left hand side variables. In the right hand side, wherever the variable, after the variable, whatever the value, based on that we can find follow of B like this. Now the production is of the form A derives alpha, variable B, beta. Now you need to find out follow of B here. How to find? Here beta is not null. The rule is here follow of B equal to this one. Non-epsilon symbols of first of beta. Non-epsilon symbols in first of beta. That is first of beta minus null. For example, here first of beta equal to plus comma epsilon, let us assume. Then non-epsilon symbols means only plus will be added to the follow of B like this. So here beta equal to not null. Beta something should be there. At that time follow of B equal to first of beta minus null. This is rule 2. This is the in examples we will see clearly. So that is rule 2. Follow of B can be found. If beta equal to null, what will happen? That is the next rule. Let us see. Then rule 3. In follow we are having only 3 rules. No problem. It is very simple. Rule 3 almost similar to second rule, but beta contains null. So the productions are of the form alpha A derives alpha B beta, or if beta equal to null means only alpha B is a production. Here beta derives null. Then first of beta contains epsilon. Then what you have to do? Here actually follow of B we need to find out. Follow of B, whatever the follow of B value, same values for follow of A also. Therefore follow of B equal to follow of A. Suppose earlier you already calculated somewhere in follow of A. Then follow of B, the same A values you can substitute here. Follow of B equal to follow of A. Using rule 3, what you will do? Already existing follow values will be useful for the current variable follow value. Whereas rule 2, you will get after variable whatever the values. If that value is not null, non-epsilon values, the terminal values will be added there in rule 2. Like that, rule 2, rule 3 you can apply for all productions by considering beta not null and beta null, the 2 cases. Now you can see some examples on this. Then you will get more clarity. Now the same problem, let us consider. This is the problem. E derives T dash, E dash derives plus T dash are null, T derives Ft dash, T dash derives star of T dash are null, F derives E within parentheses already. For the same problem, first values we already calculated. So now, for follow compulsory first values required. Why? Because in the follow rules, first values also used. Okay, now as usual, you can write down first values first, then apply the follow rules. Now let us see the first values. Directly I have taken. Why? Because previously we already did the same example. First of E equal to actually first of T. What is first of T? First of F. What is first of F? Left parenthesis ID added. Then first of T dash plus command. First of T equal to first of F. First of F we already calculated. Left parenthesis ID. Then first of T dash star comma null. Then first of F left parenthesis comma ID. These values directly written. In the previous we already did. Now coming to the follow values. In follow value rule 1, for starting variable follow of the starting variable equal to $. Here you can see rule 1, $. Is placed in follow of E since E is the starting variable. Therefore follow of E equal to $. So then you can apply rule 2 and rule 3 for the variables wherever right hand side variables are there. For T dash, here also T dash, FT dash, E. So for all these, both rule 2 and rule 2 you can apply, whichever applicable. Then coming to rule 2. So rule 2 and 3 apply for every production of the form A derives alpha B beta, where B is non-terminal. So rule 2 you can apply whenever beta is not null. Then rule 3 you can apply whenever beta is null. Now you can see in the tabular format all I have listed at one place. Carefully you can observe. Here rule 2 in first column, rule 3 in second column. So rule 2 the general format. A derives alpha B beta, beta not equal to null. Whereas rule 3 alpha B beta, beta direct beta null or beta derives null. So in rule 2 case, here follow of B equal to first of beta minus null. In rule 3 case, follow of B equal to follow of A. Now you can see take all the productions. The same production apply rule 2, rule 3 also. So then here you can see first A derives T dash. Now you are finding follow of T here. Why? Because it is in the form of alpha B beta. Here alpha is null. Okay, now B equal to T now. Beta equal to E dash now. Now beta not null. It is a variable E dash. It is a not null. Then here B is T, beta is E dash. So as per rule 2, what you have to do? First of E dash minus null will be added to follow of B. Here follow of B means T. Therefore follow of T equal to first of E dash minus null. What is first of E dash actually? We are having in the table we already listed. First of E dash equal to plus comma null. So excluding null, what is first of E dash plus? Plus is added to follow of T. Therefore follow of T equal to first of E dash minus null, T is added. The same you can apply for rule 3. Here again alpha null, alpha whatever, even null also you can consider. Our concentration is B beta. Always we can consider B beta. Rule 2 beta is not null, rule 3 beta is null. Now alpha B beta, B is T, now E dash, that is the beta. Okay, now here beta derives null. Why? Because we are having the production. E dash derives null. So whenever you can substitute this, what you will get? Beta is null here. Now you will get only B. After B nothing is there. Then what the rule we have written? Follow of T equal to follow of E. As per this, follow of B equal to follow of E. So therefore follow of T equal to follow of E. But initially we don't know follow of E. Keep this relation. Later once we obtain follow of E, then automatically T will come like that. Then coming to the same in second case.
Sir, in that follow of T equal to follow of E dash, no sir, there.
No. Not this one, left hand side. Your rule you can see. A derives alpha B beta. If beta is null, fall of B equal to fall of A, this one. But because if beta is null, nothing is there now after B, then we are depending on the fall of A values. That is the rule. The rule as it is I have written, let us see this one. We are following simply the rule. Then coming to, suppose now you can change the alpha B beta values. Let us check what will happen. Suppose E derives T E dash. Now I assumed alpha as T, B as E dash. Now beta is null. Here beta is null means rule 2 is not applicable. If beta not equal to null only, rule 2 is applicable. Then same we can apply for rule 3. So now alpha is T here, B is E dash, beta is null now. Okay, now here as per this rule, fall of E dash equal to fall of E here. All these relations further useful after calculating other follow values using rule 2. Okay, now that is for E derives T dash production only. Till now we applied 2 times. So rule 2 two times and rule 3 2 times we applied by changing alpha beta values. Then coming to next production, let us see what will happen. So first you can write down the rule and you can substitute the values. Then you won't get any confusion as per the rules. The next production, E dash derives plus T dash we have taken. Now apply rule 2 for this. Now alpha is plus, B is T, beta is E dash. Beta not null. Why? Because E dash is variable is there. So now here fall of T equal to first of E dash minus null. So here fall of T you will get plus here. Then same we can apply for rule 3. Then what you will get here, E dash derives null. Then fall of T equal to fall of E dash. One relation you will get. Similarly, for same production, apply rule 2 by changing alpha value. Suppose plus T as alpha, B as E dash, beta is null. Beta null means not applicable. Now same you can apply here. Now fall of E dash. After E dash null is there. Fall of E dash here no meaning. Why? Because E dash same you are getting. Okay, like that. Sometimes there may be chance of having some values. If we can apply rule 2, rule 3 for all possibilities, then we won't miss the values actually. Then coming to T dash production, T dash derives star F T dash, fall of F equal to first of T dash minus null. Here we will get star. Same we can apply rule 3. If T dash derives null, then fall of F equal to fall of T dash. Then for this by changing alpha values, rule 2 not applicable. Then here also by changing alpha value, here also same value you are getting. Now finally you can combine all the values, whatever the follow values you will get, all follow of E, all follow of F, all follow of T, you can combine. Then the last production, F derives E within parentheses. Now E, this follow values you need to find out, beta not null. First of beta, first of right parenthesis, first of terminal only. Therefore follow of E equal to right parenthesis, you will get. Then here you can apply rule 3 for this. Here rule 3 is not applicable actually. Here beta is not null, it is a terminal. Now E value, previously we got one value, here we got one value, and we got dollar also. Now all combine fall of E values. Once you know fall of E value, then according to rule 3 we got some equivalence values. Now you can see fall of E by default dollar we got, then right parenthesis. So then we are having the relation fall of E equal to fall of E dash. So this one. Then fall of T we got one value. Then fall of T equal to, we are having fall of E relation. Then dollar right parenthesis also added. Plus is direct value we got. Then E value also. Then fall of T dash equal to fall of T, as per the rule 3 relation we are writing. Then fall of F, here what we got, previously we got some star value. Then fall of F equal to fall of T or T dash is there earlier. So all values are added like this. can go back and check all these values. Okay, now once you know the first and follow values, then you can construct the predictive parsing table easily. We are having one algorithm. The predictive parsing table we already discussed in the model. Coming to the algorithm. So for this, input is grammar, the output is predictive parsing table. What is the procedure? The rule 1. For each production is of the form A derives alpha. For each terminal in first of alpha. For each terminal in first of alpha, first of right hand side, whatever the terminal value, in the table, A on this terminal add this production. See, the table is like this. This is terminal A, this is variable A. Now you are finding first of A. Actually, having this terminal right hand side. This is the production A derives alpha. First of alpha contains a terminal A. Then the entry A on terminal A. A on terminal A, add this production. A derives alpha. In the table, the entries are productions or blank entries. That is rule 1. For all terminals, you can apply rule 1. Then rule 2, first of alpha contains epsilon, the right hand side. First value contains epsilon. Then for each terminal B, what is B here? Follow of A, left hand side follow value. So now you can find out follow of A. Follow of A equal to, let us assume B. Then the entry A on B, you can add this production. If epsilon is in first of alpha, dollar is in follow of A. Then in this case, A derives alpha is added to the entry M of A comma dollar. In the table, you can add dollar also. Dollar also one entry. That is rule 2. Now let us see. For the same problem, only 2 rules we are having. One is the direct terminal, second case null. So the question you will get examination like this is one important standard problem. Construct the predictive parsing table for the following grammar. E derives T dash, E dash derives plus T dash, so and so. See directly, sometimes they will give the grammar with left recursion. If any grammar having left recursion, ambiguity, we can't apply predictive parser. The difficulties in predictive parser we already discussed. The grammar does not contain ambiguity. The grammar does not contain left recursion. Then non-left factored. All we have to consider. But this grammar is non-left recursive grammar only. Now you can see directly continuing with first and follow values. Then the table. First, the productions are of the form A derives alpha. Rule 1, terminal. A derives first of alpha. A is the terminal. So now here, first of E, what is first of E? Left branch is ID. Now in the table, E on left branch is E on ID. Add this production. That is M means table name. M of E comma left branch is add this production. Rule 1. E derives T dash. Then ID is next terminal. E M on E on ID. E derives T dash. Same rule 1. The second production E dash derives plus T dash. What is this first value? Plus. So M of E dash on plus, add this production. That is M of E dash on plus. E dash derives plus D dash, rule 1. Then coming to rule 2, right hand side. For null productions only you can apply rule 2. E dash derives null. Then follow of E dash we have to find out. For this, add this null production. Follow of E dash right branch is dollar. M of E dash and right branch is equal to E dash comma null. E dash derives null, rule 2. Then M of E dash comma dollar. In the entry E dash and dollar, E dash derives null is added. So like that for all the productions, you can apply rule 1 and rule 2. Rule 1 only for terminal, rule 2 only for epsilon. Similarly, T derives FT dash. First of F, left branch is ID. Then T on left branch is T on ID. Add this production. T on left branch is T derives FT dash. T on ID, T derives FT dash, rule 1. Then T dash derives star FT dash. Here first of alpha, first of star star, T dash on star, add this production, M of T dash comma star, T dash derives star F T dash. Then T dash derives null, fall of T dash value you can find out. Fall of T dash equal to plus right parenthesis dollar. All these entries, T dash on plus, T dash on right parenthesis, T dash on dollar, add this production. T dash derives null by rule 2. Then what are the other productions? F productions. Next F productions. F derives E within parenthesis, first of alpha left parenthesis. F on left parenthesis, add this production. Rule 1. F derives ID, this is also terminal. First of ID, ID. F on ID. Derives, F derives ID is added. Here rule 2 is not applicable. No null production for F. Now all these entries now you can fill in the table. Now how to take the table structure? All the columns you can take all the terminals followed by dollar. Then all the rows you can take all the variables in the grammar which can be occurred in the left hand side. This is the table structure M. So row values all are terminals including dollar. Dollar is default. Why? Because this is the end marker. Then all terminals in the grammar you can add. Then row values, all the variables in the grammar. Your grammar having unique variables E, E dash, T, T dash, F. Now the entries in the above, whatever we calculated E on ID, then E on left parenthesis, E dash on plus, E dash on right parenthesis, E dash on dollar, etc. Now all the blank entries denotes error here. The entries in the predictive parsing table, combination of a production or a blank entry. So here blank denotes error. This is the predictive parsing table. Now in this predictive parsing table, you can define LL1. What is LL1 parser actually? Here first L stands for left to right scanning of the input. Second L stands for leftmost derivation. One is the look ahead symbol. Look ahead, one input symbol is considered. So actually, when you can say a grammar is LL1 grammar, by constructing the predictive parsing table, if the parsing table does not contain multiple entries, see all the entries consisting of a single production here, single production. Suppose somewhere you are having, let us assume, so here T dash there is, suppose T dash there is null is also. Here two entries are there. If any predictive parsing table like this, then we can say this is not LL1 parser. The LL1 parser means again you need to construct the table like this by seeing multiple entries. If in at least one entry contains multiple entries, then this is not LL1 parser. But all entries are unique, no multiple entries, then you can say the predictive parser is also called as LL1 parser by satisfying this condition. Here you can see the same is given here. First L stands for left to right scanner input, second L leftmost derivation. That digit 1 indicates the one input of look ahead. That is used to make parsing decisions using that input symbol. In predictive parsing table, if there are no multiple entries, then the given grammar is called LL1 grammar. If multiple entries are presented in the parsing table, then the grammar is not LL1. The predictive parser accepts only language generated by LL1 grammar. Okay, now one more example problem I have given here. The same process, and here some of the grammars are not LL1. Any ambiguous is not LL1. Any left recursive is not LL1, and non-left factored also not LL1. Now the second example, this is also a standard question. S derives ICTS or ICTS yes or A. T derives B. Is the grammar LL1? The question will be given like this. So the same process. First you can see this grammar actually. S derives ICTS, ICTS. Here this is not left factored. ICT, yes, ICTS is repeated. Common prefixes are there. We have to remove by applying left factoring. This is not left factor grammar. eliminate left factoring by taking common ICTS S dash. S dash there is epsilon or yes after this whatever. This is the resultant grammar after eliminating the factoring. Okay, now anyway here left recursion is not there, only left factoring we have to apply. Now after that same you can find out first and follow values, the same process, first and follow values are there. Then the predictive parsing table directly I have written. Here you can see. Now is it LL1 grammar or not? How can you find? Here you can see we got two entries on the S dash on E. M of S dash on E. We got two entries. S dash derives yes, S dash derives null. Any one entry, if it contains more than one value, then you can say that is not LL1 grammar. Here you can see. The above predictive parsing table, M of S dash comma E, contains two entries. So the given grammar is not LL1 grammar. Like that you can define. Whenever dot is moved, after that if a variable is there, then what you have to do? You can apply again closure function. So like that, go to function we can apply over one grammar symbol at a time only. E means wherever dot is before E, in all items you can shift after E. So this is one. Next another one, I2 again go to off from I0 only. Over E is over. Then over T is also there. Over T we are having two places. E derives dot T derives dot T into F. Now dot place after T. Now this will be next item. Go to off I0 on T. Here you can write and again you can apply closure rule. Then I3 again go to off I0 after T over then after F. Dot is before F. Now it moves after F. After F only one you will get. Then even terminals also you can take. Then go to off I0 on left parenthesis. Now dot moves after left parenthesis. Again apply. Whenever dot is moved over a symbol, compulsory you have to apply closure rule. Then F derives dot ID. Here dot moves over the terminal ID. Go to off I0 on ID. See from I0 you are getting I1, I2, I3, I4, I5. These 5 new items are getting. Again you can continue with I1. Wherever dot is there before a symbol you can move. Again new item. Then I2 also. Like that this process will be repeated till all the items should be completed items. What is meaning of completed item? Dot should be placed at the right end. Dot should be placed at the right end in all items. Till that we have to continue. Now you can see whatever I explained stepwise. So here I have given. First I0 on E. That is I1 item. Now dot moves after E. That means in I0 dot is there before E. Now two places we are having dot before E. Now moving after E, E dash derives dot E. Earlier it is here. Now it moves over E. Now after that nothing is there. Now closure function is not applicable. After that if a variable is there then only closure function is applicable. The next one in this before dot here dot E plus T now moves after E. E dot plus T. After that we are having terminal. It is not a variable. Here closure function is not applicable. Only these items. Further no new items are added. This is called as I1. Go to a I0 on E. Similarly, go to a I0 on T. So that item we can name it as I2. Previously we are having dot before T. Now it moves here. After that nothing is there. No new items are added. Then T derives. Previously we are having dot T into F. Now dot moves after T. So now it will become T dot star F. But after dot terminal, no new items are possible by using closure function. Similarly, go to a I0 on F. We are having previously T derives dot F. Now dot moves after F. After F nothing is there. Now no new items are added. This is I3. This is completed item actually. Further we can't apply the closure function this one. Wherever dot is there in the right hand side. This is also completed item. But for this we have to apply again. This is completed item. Again T dot star. For this we have to apply. Why? Because dot moves over star. again over F like that, but only one movement in one step only we have to do. Next, similarly, I naught on terminal left parenthesis. We are having earlier F derives dot open brace E. Dot is before the left parenthesis. Now it moves after left parenthesis. After moving dot over left parenthesis, we are having variable E. Again, E items are added from the original grammar by putting dot in the right hand side beginning. Now E derives dot E plus T, E derives dot T. The same process repeated. Now you can see dot E, already E items are there. Dot T. Now T items you can add T derives dot T into F, T derives dot F. Again dot T, T items already there. Now dot F, F items are not there. Add F items. F derives dot left parenthesis, E right parenthesis. F derives dot ID. But dot terminal, further no new items are added. This is I4. So I naught on left parenthesis over. Next I naught on ID. So previously we are having in I naught F derives dot ID. Now this will become F derives ID dot. That you can name it as I5 item. Here you can see. So go to of I naught on ID. Now dot moves after ID. F derives ID. Further nothing is there. No new items are added. This is completed item. All completed items, further we can't apply the closure function or go to function. Once dot is moved to the right end. Now I naught is over. Then go back and check I1. Now I1 also, wherever incomplete items are there, for all again you can repeat the same process. Now you can see we are in I1. E dash derives dot E completed item, but E dot plus T is not completed item. So here you can see E derives E dot plus T. It is incomplete item. This is in I1. Now you can apply go to function of I1 on where dot moves over plus. This you can make it as some, what is the number? I6 or I7, whatever. Continue with the number. Now this is equal to go to of, this is some I6, let us check. Now here E derives E plus dot T. Dot moves after plus. Again after dot variable T is there. Add T items. We are having T derives T into F by putting dot. Then T derives F. Again here you can see dot T already there. Dot F you can add. So F derives open brace. Then F derives dot ID. Now this is go to of I1 on plus. Then from I1 only 1. Then coming to I2, from I2 you will get over star. So what is this item number where we stopped I naught? Let us see. Continue the number. It keep on repeating this process. Items will be repeated later. So now this is I6 what we find till now. Next coming to I7. I7 from I2 item we have to continue. So now I7 from I2. Here go to of I2 on the dot moves over star now. Now this will becomes T derives T dot star F. See after dot F is there variable. Again add it items by putting dot. The F productions from the augmented grammar. Now this is over I7. Then coming to I3, this is completed item. Here further no new items are there. Then coming to I4, here I4 many possibilities are there. Why? Because I4 on E is there, I4 on T is there, I4 on F is there, I4 on left parenthesis. This item maybe you will get repeated one again. For example, let us see I8 from I4. Go to of I4 on E. What you will get? Dot moves after E. Here you will get F derives E dot. Dot moves after this. After that at the terminal, no new items are there. Then again here, what you will get? E derives E dot plus T. So after dot terminal, no new items are added. So only these two possibilities are there over E. Further, no new items are added. This is I8. So then coming to I9, from I4 only over T you can take I9. Go to of I4 on T. Now dot moves here T dot star F. Now you will get E derives T dot, then T derives T dot star F. After that nothing is there. Here after that terminal, no new items are there. Then coming to I10. Now over T is over, then over F you can take. Here only one possibility is there. Now T derives F dot. Here you can see go to of I4 on F. What you are getting? T derives F dot. This item already there. Let us see I3. T derives F dot. Wherever repeated item is there, you can take the same name. What is the name here? I3. So, but in the table, SLR parsing table, we can't consider I10. Why? Because this is same as I3. Don't give number for this. At the time of SLR parsing table, take only unique items. Now go to of I4 on F, you will get I3 only. This is not a new item, already existing item. Then over left parenthesis, here, go to of, if it is new item, continue the item number. If it is repeated item, don't give the item number. I4 on left parenthesis. Let us see first what you will get. Dot moves after E. F derives left parenthesis dot E. So dot E means again E items are added. So E derives dot E plus T. E derives dot T. Again T derives. See again what is this one you can see. This is same as I4 only we are getting. Here you can see you will continue same as I4. So I4 on left parenthesis equal to I4. This is also repeated item. Like that we have to repeat this process for all the items wherever the dot is not at the right end. So finally what you will get, here you can see whatever we explained. I4 on T also you are getting the same. I4 on F you are getting I3. I4 on left parenthesis just now we have seen you are getting the same I4. If any unique item you can continue the item number. If it is repeated item, don't give the number. Why? Because for SLR parsing table, you can take unique items for the construction. Now you can see I4 on ID, we are getting same as I5. Then I6 on T, this is a new item actually. So you can continue the number, but here the numbers are continued, but table construction, these duplications you can remove. Now I6 on T, this is a new item. Then I6 on F, you are getting I3. I6 on ID, you are getting I5. Then I6 on left parenthesis, you are getting a same as I4 only. Like that, this process you can repeat for all the items till dot is moved to the right end. Now, I7 on F, you are getting new item. I7 on left parenthesis, you are getting I4. Then I7 on ID, you are getting I5. I8 and right parenthesis, this is new item. New item. I8 and plus, you are getting same as I6. So like that, you can repeat this process. Then another one, some I13 on star, you are getting the same as I7. With duplication here, total I0 to I22, 23 items are there. By excluding duplication, the unique items that can be included in table construction, SLR parsing. Once all the items are constructed, now you have to construct DFA. How to construct DFA? For the canonical set of LR0 items. So the item I0 considered as the initial or start state. You can make it as this is one. Then go to function over all the grammar symbols, not only terminal, over variable also. So go to of some I0 on E equal to some I1, let us assume. So this is nothing but delta of I0 on E equal to I1. This is the transition. Like this you can write down. The go to function. Now you can take, so this is I1. I1 is the next new state. So here the same as transition diagram. Now I0 on 0. Similarly delta, then go to of I0 on T. This is some item 2. So then another one I2 take here on input. What is the input here? The terminal T. Here don't think in our automaton inputs are only sigma. But here in the LR0 automaton, the items, the inputs are both variable as well as terminal. You need to consider here. So like that. Now you can see the final DFA diagram shown here. So LR0 automaton. Here you can see. So first initial item I0 we have considered as the initial. So here I0 followed by all the items also you can list out. Now I0 on E, that means go to of, this is nothing but go to of I0 on E equal to I1. So here I0 on E, it is going to I1. Then go to of I0 on T, it is going to I2. Go to of I0 on F, it is going to I3. Then go to of I0 on left parenthesis, going to I4. Go to of I0 on ID, it is going to I5. Then again from state 1, item 1. So go to of I1 on plus equal to I6. So then only one item is there. Then I2. Go to of I2 on star, it is going to I7. Then here also only one is there. Then I3. From I3, this is a completed item, no transition. Then I4 on left parenthesis, the same loop. I4 on ID, it is going to I5. Then I4 on E, it is going to I8. So like that, same as our TFA automata. How to construct a transition diagram. Transition table not included here, only transition diagram used for LR0 items. Like this, we can construct the DFA automaton for LR0 items. Now with these items, now how to construct our SLR parser. Before that, this is the common model of LR parser. Either simple LR or canonical LR or look ahead LR. Same model we have to follow, but only parsing table SLR, CLR, LLR with action go to. This parsing table having two parts, action part, go to part. We'll see about this also. This is the model. You can see the predictive parsing model similar to that. There we are having predictive parsing table, here LR parsing table. Here also stack is there, input or input buffer is there, here stack symbols, but these are all states. Whereas in a predictive parser, what stack contains grammar symbols, but here it contains states. So state 1 to state n, that means item 1 to item n, 0 to n, the suffix values are states will be used here, like state 0, that is S0, state 1, state 2, and so on, state n. These are all the state values. Here input contains same as input symbols only, ended with $, that is end marker. Here their predictive parsing program, here LR parsing program, here output. Parsing is successful or not. Then parsing table, where predictive parser, that is two-dimensional. So here this table having two parts, action part and go to part. For all the three types of parsers, same action go to values are there, but the construction process is changed. For all parsers, this is the common model. Only parser to parser, the table is different, but the table structure is also same action and go to part. Now you can see the LR parser consisting of input, output stack, then parser program, parsing table. It has two parts, action and go to. The parser program same for all LR parsers. Only parsing table changes from one parser to another parser. The parsing program reads character from the input buffer one at a time. Where shift reduce parser, that means here shift action, reduce action. Shift a symbol, then an LR parser shifts a state. So shift will denoted with S followed by the suffix state number. This is state. For example, shift I, this can be written as S suffix I. Shift 1, this can be written as S1. So S means shift, suffix means state number. Then another value reduce denoted with R with the production. For example, E derives E plus T. So actually reduced by this production. What is the number of this production? For example, in the given grammar, original grammar, whatever the production number, suppose R1, then reduced by second production R2, reduced by third production R3, reduced by fourth production R4. These are all reduced values. These are all shift values. Then next value accept. This can be denoted as AC. Next value error. This can be denoted as ERR. So in the parsing table, first value is shift value denoted with S suffix I. Second value reduce denoted with R suffix state number. Then third one accept. Fourth one error. Error means all the blank entries. So any LR parsing table which is combination of these four values only. Now how to construct SLR parsing table? Let us see. First the algorithm. The parsing table algorithm is also almost same. Only in SLR parser LR0 items are there, whereas CLR, LALR, LR1 items are there. How to construct LR1 items that we will see after completion of this SLR parser. The four values what I explained same. Now the action part in the table, action part, go to part. Action part will contains terminals plus dollar, go to of only variables. Only variables. So action part contains the predictive parsing table like. So variable combination, terminal combination including dollar. Whereas go to part only the variables like delta of Q0 on 0 equal to Q1. Here go to of I0 on 0 equal to I1. So from state 0, this is the variable, let us assume 0 on E, the state is 1. In the table entry, only the state numbers you can enter. Go to values are states. Then action part, the four values what we discussed. That is shift, reduce, accept, error. These are all action values. Go to values only state numbers. Here you can see go to of II, A equal to IJ. Only over variable we have to consider, not terminal in the table. That means from item number II on the variable A, it is going to item number J. That means suffix small I is the state I. On variable A, it is going to state J. That value you can enter in the table. Now see the construction algorithm. Then we will see with this LR0 items how to construct the table. Constructing SLR parsing table with the following steps. For the given grammar, first augmented grammar you need to find out. For the augmented grammar, find out LR0 items. These two already done. The above. Then first and follow also the predictive parser, same process you can use find out. Then parsing table using the algorithm. Here again, the fourth point only we have to do now. To construct SLR parsing table, previous three steps you need to perform. Then finally use this one. Now you can see the algorithm name SLR parsing table for augmented grammar. G dash is the input. Then output SLR parsing table with action and go to part. But in the parsing table, production number should be from the original grammar, not from augmented grammar. Original grammar without introducing new starting variable, those numbers only you have to give in the reduction values. So first, the procedure step 1, obtain LR0 items or canonical collection of sets of items that can be stored in the variable C for the augmented grammar G dash. Let the items be C equal to I0, I1 and so on IN. These are all unique items. Previously we got 23 items. You can take only unique items. Now the suffix values 0 to N, 0, 1 to N will be the states of the parser. The parsing action for each state I can be obtained using the following rules. Okay, now the first rule, if the item is like this, A derives alpha dot terminal A beta is in some item number II. Here you can see after that a terminal is there. Then go to of II means this item. over A, terminal A, it is going to which item? Some ij. Now you can see the action value, how to fill. Carefully you can observe. From this go to function, the action value. Action of first value is state, second value is terminal or dollar also. Now in this, what is the state suffix value? I. So action of small I, the terminal is A here, equal to here J. But here what is this one? State J. State means we have to write shift J. Nothing but S suffix J. Now in the table, let us see action of I on A, shift J, where A must be a terminal here. After dot a terminal, then only you can apply rule second step, first rule. For all terminal combinations, you can apply this one. Here, like this, you can fill the shift values. Similarly, next, if item will be completed item, A derives alpha dot. After that, nothing will be there. Is in some item number, then you have to find out follow of left hand side variable A. So that value should be, let us assume, small a. So small a in follow of A, so then action of the state suffix I, comma the terminal follow value equal to, here it is not a state, here you will get reduction. For completed item, you will get reduced values. Then the items where dot before terminal, you will get shift values. Now here you can see action of I on terminal A reduced by this production. A derives alpha. What is the production number actually? That number you have to give. For example, this is 1. So R1 you have to give in the table. That is the reduction value for completed items. So then the rule C in step 2, this is only for the special item. S dash derives S dot. For a new starting variable S dash, completed item is in some item number. Then I on lookout symbol dollar you can take. Then don't take follow of S dash. Why? Because S dash there is S dot. So that is the default n marker dollar is added. Now action of I comma dollar equal to accept. For accept only one time it occurs. This value occurs only in one time. Only for this item, completed item, that starting variable. New for augmented grammar, starting variable completed item. S dash is S dot. So here suffix I, the look ahead dollar default, comma, action of I comma dollar equal to accept. Now shift value is over, reduce value is over, now accept value is over. After filling all these three values, all the blank entries, nothing but error. But specifically we won't mention error, we will keep it as blank only. By default, blank means that denotes error only. That is action part. Then how to fill go to part? Just now I already explained go to part. Starting go to transition like delta function. So go to of I comma variable. For go to values you can take only variable, not terminal combination. So go to of I comma a equal to ij. Nothing but the suffix state I on variable a. Here you can see in the go to part. Go to part only variables it includes, not terminals or look ahead. So now from state I on variable a, the next state is j. So here don't use shift j, reduce, accept. Only j only you can include. For example, you are having the item like this. So go to of I naught on e equal to some I1. Now in the table 0 on e, you can include the 1 only. Don't include shift, reduce, accept, error. Only state number, suffix value only you can include in the go to part. So now a special item, if II contains S dash 0 S dot, then I is the initial or start state of the parser. In the DFA of LR0 items we already discussed. So how to identify the initial statements? If any item contains S dash 0 S dot in a particular item number, then that will be treated as the initial or start state of the parser. Okay, now after constructing the SLR parsing table, same as LL1, no multiple entries, no multiple entries in predictive parser, predictive parsing table, then that is LL1 grammar or parser. Similar rule applied for all the LR parsers. In SLR parsing table, if there are multiple entries in the action part, here you can consider only action part. In the predictive parser, we don't have a separate category, common values only. But in the LR parsing, two parts, action part, go to part. In the action part, if there are multiple entries, then the grammar is not SLR1 grammar. If no multiple entries in the action part, then that is called as SLR parser or SLR1 grammar. The parsing table obtained using this algorithm is SLR parsing table, and the parser which uses this table SLR parser, the grammar is said to be SLR1 parser by default. So LRK default value is 1. Default is 1. That means SLR1 parser, CLR1 parser, LALR1 parser. Similar definitions applicable here. SLR parser, SLR parsing table. CLR parser, CLR parsing table. Only the respective tables needs to be considered. LALR parser, LALR table needs to be considered. Now using this algorithm for this problem, let us see how to construct the table. So the question will be given in examination like this. Construct SLR parsing table for the given grammar. Directly, if you can see, the starting variable doesn't occur anywhere in the right hand side, means you can consider it as the augmented grammar. If at least one production in the right hand side starting variable occurred, then you can convert into augmented grammar. Then that is not augmented grammar. Now here you can see this is not augmented grammar. E occurred here right hand side, first production, then F production also. So for this we already augmented grammar is constructed, G dash, by introducing new starting variable. Then LR0 items also constructed. So your first and follow values you can find first of E, T, F. So this is even here left recursion is there. Why? Because in bottom up parser we don't have restriction of if it is not no left recursion, not ambiguity, ambiguous, no restrictions such. So even whatever the given grammar, even having left recursion, you can find out first and follow value. Only in predictive parser we have to stick on the limitations of top-down parsing. It doesn't allow left recursion, then ambiguity, all we have to remove. But in bottom-up parser there is no such restriction. Directly we are finding first and follow values, ETF. So first values, follow values, using the same rules. Okay, now let us come to the LR0 items. I0 to I22 we already constructed now. From I0 to I22, the same I have listed here. By repeating duplications, let us see the unique items. By removing the duplicates, here you can see, here we have listed I0 to I11, 12 unique items are there. From I0 to I22, after duplicate items removed, the unique items are stored in C, I0, I1, I2 and so on I11. Now 0, 1, 2, 3 and so on 11 are states of SLR parser, SLR parsing table. Now the rules now we will apply here one by one. First step 2, rule A. If you are having goto function like this, goto of I comma A equal to ij, that is dot is placed before terminal, then that is going to a particular item. Then action of the suffix I comma the terminal A equal to shift j. Now we are having over terminal combination only you can consider, not variable. Here A should be a terminal. Now all the goto values we have taken like this, direct values. Here already function is there. Go to I naught on left parenthesis, it is going to I4. Now in the table action of 0 comma left parenthesis equal to shift 4 means this is nothing but shift 4. That can be written in short forms S4. 0 on left parenthesis. Then I naught on ID I5. 0 ID equal to S5. Then I1 on plus I6. 1 on plus equal to S6. These are all action values. We are filling action part of the table. Over terminal combination first we are taking. Then I2 on star I7. Then 2 on star equal to S7. Then I4 on left parenthesis I4 loop. 4 on left parenthesis S4. Then I4 on ID I5. 4 on ID S5. Then I6 on left parenthesis I4. 6 on left parenthesis S4. Then I7 on left parenthesis I4. 7 on left parenthesis S4. See here, even repeated items also we have to consider here. So why? Because in the automation also self states occurred on particular input going to the same state. But item number should be unique. Repeated items without state number, whatever the repeated item number, that item we will take. Now similarly I7 on ID I5, 7 on ID S5, 8 on right parenthesis S11. Then similarly I8 on plus we are having 6, 8 on plus S6, I9 on star I7, 9 on star S7. That is rule 2A. Then coming to 2B, 2B is applicable for only completed item. Wherever dot will be in the right end in any item, for all you can apply rule 2B. Now here what you have to do, fall of A we have to find out. Here you can see small a equal to fall of A. Whatever A is not a single value, even you will get more than one value also. So A equal to fall of A, then what you have to do? Whatever the item number suffix I, small I, action of I, comma the follow values, the same value. Action of I on follow value A equal to reduce. For completed item, only reduced values will be generated. Reduced by the production name we have mentioned, but the table we can give the numbering of the production. The numbering will be given from the original grammar. That is not for augmented grammar. You are given original grammar. By default, the original grammar itself is augmented grammar. Then you can give the production numbers for the same. If the given grammar is not augmented grammar, you need to find out new grammar by introducing new starting variable. But production numbers you can consider only for original grammar. Now here you can see the first completed item E derives T dot in I2 item. In I2 it is there. In the above, from above we are doing this one. Now fall of E you can find out. Fall of E also we listed plus right parenthesis dollar. Now the action entry with the same state to on plus on right parenthesis on dollar. From the state with 3 different terminals, the same production we can use. Reduce E derives T. Now you can see in the action part 2 state, this is state. Then the terminal values including lookahead. 2 on plus or E derives T. 2 on right parenthesis same production. 2 on dollar same production. So E derives T, what is the production number actually? You are given original grammar E derives E plus T, then E derives T, T derives T into F, T derives F. Take all the production separately, even starting with same variable also. Separately you can list out the production numbers 1, 2, 3, 4, 5, 6. Now you can see E derives T, what is the number 2? So R2 is used here, R2. Similarly, next T derives F dot is in I3 item. What is follow of T? So follow of T equal to star plus right parenthesis dollar. Now 3 on plus 3 on into 3 on plus 3 on right parenthesis 3 on dollar. So what is the production here? T derives F. T derives F equal to fourth production. So R4 you can use like this. For all completed items, you can take the reduced values. Similarly, F derives ID dot is in I5. Now follow of F plus star plus right parenthesis dollar. 5 on star, 5 on plus, 5 on right parenthesis, 5 on dollar. By the production F derives ID. F derives ID, what is the number? 6th production. So R6 you can take. So like this you can fill all the reduction values. Similarly, E plus T dot, then T derive T dot F dot, then E right branches dot like. So all the reduction values you can fill. Then coming to 2C rule. The 2C rule only for one item we will get, that is for special item. S dash derives S dot is in some item number. Then this item number comma dollar. The 2C rule we already discussed. The action of I comma dollar equal to accept. This will be occurred only one time. Only for this item will be occurred only one time. Now in our items E dash derives E dot is in some I1. Now 1 on dollar equal to accept. Now shift value is over, reduce value is over, accept value is over, then all blanks denotes error. These are all only action values till now. What we constructed only action values. Then coming to go to, that is direct delta function. I already explained previously. The go to rule, go to of I comma variable, only variable you have to take, equal to ij. Then from state I, variable a, the next state is j. Only state number you can give. Now I naught on E, it is going to I1. Then 0 on E equal to 1. Then I naught on T, it is going to I2. 0 on T equal to 2. I naught on F, it is going to I3. 0 on F equal to 3. Then I4 on E, it is going to I8. 4 on E equal to 8. Here only you are getting single state values. Like for all variable combination, go to function. Then I4 on T, I2. Then I4 on F, I3. And so on I7 F, I10. Now you can see after finding all the action and go to values, now you can construct the table by entering those values. This is the structure of SLR parsing table. We already mentioned action part only terminals, including dollar. Go to part only variables in the original grammar, not augmented grammar. Your original grammar contains E, contains T, contains F. Only 3 variables. So ETF. Now all the states are, see, we assumed unique items I0 and so on I11. The suffix values 0, 1, 2 and so on 11 are the states here. Here you can see 0, 1, 2, 3. These are all unique. Now just now we calculated action value 0 on ID, so and so on. Then go to values also we calculated. Here you can see accept occurred only one case, only one place it should be occurred. Then shift values, then reduce values are there. Then go to values only state numbers. Then all the blanks error in the action part. Why? Because for parsing action, we'll take only action part values. Action part. Go to also wherever blank, but error only, but this will neglect. Only action error we will consider. So this is the SLR parsing table. Now check out, is there any multiple entry? Even combination of shift reduce value also more than one value. Even different values also more than one entry in one particular entry. So here all are single values are there. All are single values are blank values only. So here no multiple entries. No multiple entries. So this is SLR1 parser. SLR1 parser. Then whatever the grammar we used, that is called as SLR1 grammar. In the above SLR parsing table, there are no multiple entries in the action part. Therefore, the grammar is SLR1 grammar. So that is the SLR1 parser. They're coming to more powerful LR parsers. This is, once you know CLR parser, LALR is very simple. With this only some modification. First, canonical LR is one of the powerful LR parser. Just LR also will call. It makes full use of look-ahead symbols. Here one symbol is used, K. This method uses large set of items called LR1 items. This is new. How to construct LR1 items we'll see. Then look-ahead LR or LALR, which is based on LR0 sets of items and may have fewer states in the typical parser based on LR1 items. So, but here we'll use LR1 items only for this. Based on this, we'll take LR1 items. Now, how to construct LR1 items. Let us see here. The algorithm, everything same here. So how to define LR1 item? LR0 items, whatever the methodology we used, everything same. The only difference here, one extra look ahead symbol will come, will be added. That is the only difference. Here you can see an item of the form A derives alpha dot beta, comma A, small a. So here A derives alpha, beta is a production. Small a is a terminal or dollar. This one is a terminal or dollar. Dollar means right hand marker. This is called as LR1 item. Here one is the look ahead of the item. So here also same as closer, go to, same as LR0 items. But look ahead symbol needs to find for every items. This is the new actually. Remaining all are same. Then how to find the look ahead symbol for every item? That is the thing we have to concentrate. So in an item of the form A derives alpha dot beta comma A, where beta is not null. This is not null. Then the look ahead has no effect. But because if it is not null means no use of this. If it is null, then only this will be used. Now, if the item is of the form A derives alpha dot, after dot beta is null here. So then A impact is used here. So then call for the reduction using the production A derives alpha. If and only if the next input symbol is A, this one. That is the use of look ahead symbol here. Now the closure function, everything same. Now you can see initially add every item in closure of I. A derives alpha dot B beta comma A. So then after that variable B items you can add by putting dot in the right hand side beginning. So then how to find out the look ahead symbol for this? So for each terminal B, what is B? After variable whatever this one, look ahead symbol combination, take first of beta A. We would add first of beta A as the look ahead symbol, assume it as B. So here B equal to first of beta A. We know how to find first value. If it is terminal, direct terminal value you can take. If it is not a terminal variable, it first value you can find out like this. So whatever the B here, that is the look ahead here. That can be added to this one. Everything same, only finding the look ahead. How to find the look ahead? First of beta A. Every time first of beta A you can consider. If beta is null also, first of null, whatever this value, then you will get this value only. Then apply this rule to repeatedly until no more new items are added. Then go to is also same. Now you can see, for example, this is one grammar. S dash derives dot S. Initially for the starting production item, dollar is added. Look ahead. This is end marker. Default look ahead symbol. Default look ahead. So now you are adding S items now. Now you can see S dash derives dot S comma dollar. Now what are the S items? Closure function. S contains dot CC. Now the look ahead you need to find out here. First of beta A. Now after S, this is beta, dollar is A. Here beta equal to null. Now what you will get here? First of epsilon A. Only epsilon means epsilon you have to consider, but here after epsilon terminal is there. Whatever that you can consider. Then first of A equal to A. Now A is the look ahead symbol. Here A means dollar. So now dollar is the look ahead symbol. Now you can see S derives dot C, variable C, again add C item, C derives dot CC, C derives dot D. For these two, how to find out look ahead symbol? First of beta A. After C, whatever this one, this is capital C. So first of capital C terminal A. What is first of C? Here we listed C comma D. Now you can see first of C comma D A. Now first of C comma D is a single first of C value. Both you need to consider C or D. First of terminal only. Okay, now here you will get C or D added. See, this is same. Only lookout symbols we are finding using first of beta A every time. That is the only. Remaining all are same. So like that you can find out all the closure values. Then go to value also same. Shifting dot over one symbol. Now directly come to the problem. So in examination you will get the question like this. For the given augmented grammar, compute LR1 items or canonical collection of sets of LR1 items. Here also you need to consider augmented grammar. Here we already given augmented grammar only. S dash not occurred anywhere in the right hand side. Okay, now first I naught how to find out. S dash derives dot S comma dollar. Default you can add only for this. Now dot S items you can add. S derives dot CC. Here first of beta dollar. First of beta dollar. Beta is null. Now dollar will come. So dollar. Now here C items. C derives these two productions by putting dot. Dot terminal C variable C. C derives dot D. Now the look aheads here first of beta A. Beta is capital C. A. First of capital C we already calculated C comma D. So same items will come CRD, CRD. Why? Because first of C contains two values. All values we have to consider here. Now this is initial item. Then I1 how to find out? Further C dot small c terminal. No new items are added. Dot D small d terminal. No new items are added. Now move dot over one symbol at a time. Now go to of I0 on S. S is occurred only one time. Dot before S. Now this will become S dash derives S dot. By default, the same look ahead will come. Whenever new items are added, you can find out the look ahead symbol. Just a minute. Okay, like this now you can find all the items. The same as LR0 only. Every time the lookaheads are added. Here also you can consider unique items only. This is the DFA for same as LR0. Now construction of the CLR parsing table also everything same. That's why once you will get clarity on SLR parsing table, remaining CLR, LALR similar. Only LR1 items are there. Now here also you can see. But here one difference you need to observe in rule 2. Here we no need to find follow value. We no need to find follow value. Why? Because here the look ahead symbols are there. In place of follow, we will use look ahead symbols. Now see 2A rule, A derives alpha dot terminal, comma B. Now go to of IA on A equal to IJ. Here you can see action of I comma A shift J. The same terminal is used here. For completed item, A derives alpha dot. Actually, in completed item, follow of A we have obtained in SLR parser. Here not required. Directly look ahead is there. So same value you can use here. Here I comma A equal to reduced by production number. That is the only difference. Remaining all are same. Remaining all are same, no changes. Only in case of completed item follow value, we can take look ahead symbol. That is the only difference. Now the question, construct CLR parsing table for the grammar. The same, first you need to find out augmented grammar, then all the LR1 items. Now you can see using the same rules. Only in case of completed item here you can see. Here we are not finding follow value. Directly we are taking the look ahead value. Now it is easy comparing to SLR. Here no need to find out the follow value. Then nothing is new, remaining all are same. Now you can see action go to part, the same. Here also if multiple entries are there, that is not CLR1. If no multiple entries, then that is CLR1 parser. Now see the look LALR parser. Here LALR parser, what we will do, everything same as CLR parser only. In LR1 items, the common cores are merged. Here you can see the items consisting of common cores. What is the meaning of common core? For example, we are having C derives dot CC, C derives dot D. You are having dollar. For example, this is I1 item. Then I2 item is like this. C derives dot CC, C derives dot D. See, the items are same, but the lookaheads are different. Now these two are merged. You can make it as new item I12. How to merge? C derives dot CC. The lookahead first one, then the second lookahead dollar or C or D. Then C derives dot D, dollar or C or D. This is the only difference. Remaining everything same. Here some items are merged. That means reduced. That is the only difference. Remaining everything same as CLR parser only. That is the only difference in LALR parser. Now in our previous example, let us see what are the items having common cores. Now here you can see. So in the above LR1 items, I3, I6 items are same, lookaheads are different. You can combine these two. I4 and I7, these two can combine. I8 and I9, you can combine. Now I0, I1, I2. Now I3 means I36. I4 means I47. Then I5. I6 already merged. Don't take I6. I7 already merged. I8 means I9. So then I10 not there. Then I11. Now these are all the unique items. The same algorithm you can use. Now you can construct its table. Look at parsing table. Now you can see. Same is used here. Here you can see 3 and 6 are merged. 4 and 7, 8 and 9 are merged. For the table construction, everything same. Now you can see this is the table. Here now states you can observe. The states are merged. 3 and 6 are merged. 4 and 7 are merged. 8 and 9 are merged. The shift values also. Suppose you may get S3 means don't take S3 separately. Whatever the combination state, that only you can take 3, 6. S4 means don't take S4 separately. The 4, 7 combination state you can take like this. So whatever here the states, the action values are combination of the same only. Here go to also. So here 8 means we don't have 8 separately. 8, 9. Here also multiple entries are not there. Now this is LR1 parser. Like that we can find LALR parser easily. That's all about the LR parser. The 3 techniques: simple LR, canonical LR, look ahead LR. With this now I am closing. So if you have any queries you can ask. So because in the entire of compiler design course, the problems will be from the second unit, that is parser only. Top down parsing, predictive parser, LL1 parser, one problem. Bottom up parsing, either SLR, CLR, LALR. Remaining all are very easy topics. Don't bother about any other topics. All are simple, just some procedure examples like that only.